কিন্তু প্রবলেম হয়েছে তো, শেয়ারেবল লিঙ্কটা বদলে গেল তো। কি করি বলো তো, কাউকে দেওয়া যাবে এখন? তুমি এখন করতে করতে পাঠিয়ে দিতে পারবে? হ্যাঁ, কি সেটাই তো দেখছি। দাঁড়াও, 1 মিনিট দাঁড়াও, আমি হোয়াটসঅ্যাপে তোমাকে পাঠাচ্ছি। হ্যাঁ, আমি মেল করে দিচ্ছি, তুমি আমাকে পাঠিয়ে দাও। হ্যাঁ, আমি করে দিচ্ছি সবাইকে ইমিডিয়েটলি। হ্যাঁ, একটা গন্ডগোল হয়ে গেছে আর কিছু, আমাদের কপাল জানো তো। দাঁড়াও, চলছে, ইউটিউবটা চলছে লাইভে। দাঁড়াও, ওটা লিঙ্কটা বদলে গেছে।
সহোদরী জয়েন করেছেন?
তোমরা একটু ওয়েট করো, আমি তোমাকে রিপ্লাই দিচ্ছি। টেকনিক্যাল প্রবলেম হয়েছে।
আচ্ছা আচ্ছা, ঠিক আছে।
টেলিগ্রামে তুমি লিঙ্কটা দিয়ে, কোথায় কোথায় তুমি ইউটিউব দিয়েছো বলো, আমি সেখানে তোমার হয়ে দিয়ে দিচ্ছি। তুমি বলো। স্টুডেন্টদের মেল করে পাঠিয়েছো? সব স্টুডেন্টদের একসঙ্গে? ওটা দিয়ে দাও, ওটা এখন দিয়ে দাও। দিয়ে দিয়েছি, দেখো তোমাকে আমি দিয়ে দিয়েছি যেটা চলছে। হ্যাঁ, ওটা দিয়ে দাও, ওটা এখন দিয়ে দাও। দিয়ে দিয়েছি, দেখো তোমাকে আমি দিয়ে দিয়েছি যেটা চলছে। হ্যাঁ, ওটা দিয়ে দাও, ওটা এখন দিয়ে দাও। দিয়ে দিয়েছি, দেখো তোমাকে আমি দিয়ে দিয়েছি যেটা চলছে। হ্যাঁ, করেছো আমাকে মেল? তুমি 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 যে করে দিয়েছো? আচ্ছা, ঠিক আছে, তাহলে আর কোনো প্রবলেম নেই, ঠিক আছে। আরে কি, আমি তখনই বললাম যে এরার দেখাচ্ছে, আরে আমরা তো সব জানি না। হ্যাঁ ওটা করছি তো, দেখাচ্ছে, দেখো দেখো। হ্যাঁ চলছে চলছে, ওটা লাইভ চলছে। আচ্ছা ঠিক আছে ঠিক আছে।
স্বাগতদি প্রিন্সিপাল স্যার জয়েন করেছেন?
না দেখতে পাচ্ছি না তো, উনি এখনো জয়েন করেননি।
হ্যাঁ অতুল জয়েন করেছি।
স্যার জয়েন
ও
করেছেন।
স্যার,
ঠিক আছে স্যার জয়েন।
স্বাগতদি তাহলে স্টার্ট করি নাকি?
হ্যাঁ করো।
স্যার স্টার্ট করছি।
হ্যাঁ হ্যাঁ ওকে।
So we'll start the event, but before that, a general announcement for all the participants. First of all, our YouTube link is not working. That is a technical problem. So I have mailed to all the student participants the new link. Please follow your mail and the WhatsApp group also. That's a general reminder to all of you. So, and sorry for that technical problem. And the participants who are in the Google Meet, so please mute your microphone first and switch off your video. Please do not share your screen throughout the event. And remember that there is no scope to communicate directly with the resource person. If you have any specific question to the speaker, you can put it in the chat box. We'll select relevant questions both from YouTube and Google Meet. All these technical instructions are given to make the event noise-free. So hope you all will cooperate with us. Thank you. So welcome to the one-day international webinar entitled Recent Trends in Condensed Matter Physics and Applications 2020, organized by Department of Physics, Kulti College in collaboration with IQAC Kulti College. On behalf of the organizing committee, I am extremely happy to share that we have received overwhelming responses from the participants from different institutions of our country and beyond our country. As per our record, we have received around 500 registration requests, not only from the students but also from the researchers and faculty members. So on that note, I sincerely want to express my hearty thanks to all the participants for showing interest in our program. As we all know that the outbreak of COVID-19 has been declared as a public health emergency of international concern, and the virus has now spread to many countries and territories. The situation is increasing almost exponentially in our country. In these pandemic situations, this health crisis is hampering the education system also. So the central aim of the arrangement of this webinar is to motivate young students and researchers. We believe that this interactive event will act as useful catalyst in their career. The young minds will get opportunity to learn the new exciting things beyond their textbook, which will make them curious about the subject of physics. Hope that this will be the best utilization of the confinement period for the learners. So now, I would request our Honorable Principal Sir, Dr. Supriyo Chakraborty, to deliver the keynote address. Sir, it's over to you.
Thank you Otunu and welcome to all the participants. First of all, I would like to convey my heartfelt gratitude to all of the resource persons over the globe for sparing their valuable time for this webinar. I also congratulate the organizer and the hearty welcome to all the participants. Now it is the time for my brief deliberation. Now what condensed matter physics is? It is the physics of solids and liquids that includes the ground on which we are standing and the screen on which you are watching me and all others. Condensed matter physics is the field of physics that deals with the microscopic and macroscopic physical properties of matter. In particular, it is concerned with the condensed phases that appear whenever the number of constituents in a system is extremely large and the interaction between the constituents are strong. The most familiar example of condensed phases are solids and liquids, which arises from the electromagnetic forces between atoms. Condensed matter physics seeks to understand the behavior of these phases by using physical laws. In particular, they include the laws of quantum mechanics, electromagnetism, and statistical mechanics. A variety of topics in physics such as crystallography, meteorology, elasticity, magnetism, etc. were treated as distinct areas until 1940s, when they were grouped together as solid-state physics. Around 1960s, the study of physical properties of liquids was added to this list, forming the basis for the new related specialty of condensed matter physics. What's the role of CMP, that is condensed matter physics, in daily life? Condensed matter physics is the fundamental science of solids and liquids. As the largest branch of physics, it has the greatest impact on our daily lives by providing foundations for technological developments. For example, the invention of transistor and semiconductor chips have led to the widespread use of variety of data storage, telecommunication, multimedia devices such as cellular phone, digital still and video cameras, MP3 players, GPS, flat panel HD TVs, DVDs, hard disk drives, flash drives, Blu-ray players, iPod, iPad, all this, and personal computer. Almost every aspect of our daily life got benefit from research in condensed matter physics. For example, composite materials are used in jet turbines and modern tennis rackets. Superconducting magnets are used in MRI tomography for medical diagnostics. Various solid-state sensor and detector for space exploration and homeland security, and laser for entertainment, broadband communication, and various medical procedures. Now, my last point of this discussion is, what is the role of condensed matter physics in this pandemic? It is known that invention of cure and preventives for any disease is an important function of structural biology. Physics-based technology plays a huge role in the field of structural biology. The vast majority of biological macromolecule structures are obtained by X-ray. Structural biology rely on mathematical tool, the Fourier transform. The calculated contribution are then equated with the possible atomic structure by a lot of careful interpretation, which is now largely been done on computer. So it can be said that condensed matter physics is one of the most important weapons for the structural biologist to fight against any disease as well as present pandemic. It is too early to predict the golden time when fully proved cure and preventives of the virus steps in to the world. Still, we hope structural biologists, with their one of the most powerful weapons, that is condensed matter physics, and continuous application of physics research, along with and its associates towards a COVID-free world very soon. That's all from my side. That's all from my side.
Thank you, sir. Now, I request Dr. Saurabh Shah, Head of the Department of Physics, to say a few words about the theme of the webinar. Dr. Shah, it's over to you.
So, thank you, Dr. Noni. So, good afternoon to all of you, and hearty welcome at the international webinar named Recent Trends in Condensed Matter Physics and Applications 2020, jointly organized by Department of Physics, Kulti College, and IQAC Kulti College. Here we have the gracious presence of Dr. Shukil Chakraborty, Chairperson RTCMPA 2020 and Principal Kulti College. We are honored to have Professor Olnavu Chakraborty from Presidency University, Professor Devnarayan Jana from University of Calcutta, and Dr. Paramita Dotto from Department of Physics and Astronomy, Uppsala University, Sweden, as our speakers. Present here, IQAC coordinator, convener, joint convener, and technical support, members of organizing committee and staff of Kulti College, and dear participants, including faculty members, scholars, and students, and to remember always our ex-students and present students, ex-students who are engaged in different universities. And without all of your cooperation, we will be able to conduct this international webinar. So, condensed matter physics is a branch of physics that deals with the interaction of the constituent particles in condensed form. It deals with the solid, liquid, plasma, and other complex forms of matter. Now, among different subdivisions under it, some are old and some have been found to be really new. Like X-ray and crystallography is one of the old soldiers of condensed matter physics. It started journey when scientist Röntgen invented X-ray and photographed his own fingers wearing the engagement ring. Since then, this has been remaining a very strong tool for determining crystal structure. Even with the advancement of SEM and TEM, X-ray diffraction, X-ray fluorescence spectrometer, and XPS, they are showing extremely useful pathways to find out crystal interior. Magnetism is another old term which is used extensively in modern life and under advanced study in its new author. We physicists particularly are always in debt to magnetism, since it was a magnetic needle which made a little boy curious and thoughtful of the existence of natural power at the age of 5. The little boy was thought to be below average by his teacher, below average student. But the unseen behavior of magnet turned the boy into a genius. Today we know him by Dr. Albert Einstein. As a new branch of condensed matter physics, the nanomaterials and nanotechnology is one of the very prominent and active field of interest. This field started its journey many years ago. The colorful glass paintings of medieval church windows, Damascus sword, Lycurgus cup are familiar examples of nanoparticle development in the past decades. However, modern nanotechnology regime started with a very popular dialogue of Feynman that few rooms at the bottom. So, nanomaterial, in short, it is a special state, intermediate between the bulk material and the atom or molecule. Whenever the particle size is within the 100 nanometer range in at least one dimension, it is termed as nanoparticles. At present, nanomaterials and nanotechnology is used almost in every aspect of modern lifestyle. A new branch has been developed as nanoelectronics that deals with the application of nanoparticle inside the electronics devices. Different new gadgets that have been developed are nano memory, nano circuitry, nano diodes and transistors, OLED or organic light emitting diodes, plasma displays, quantum computers, nano sensors, etc. Carbon nanotubes have been used to develop field electron transistors. Single electron transistor is another fast functioning device which is operated by means of a single electron. With these inventions, the science and human life have been furthered a lot. Another important application of nanotechnology finds in medical field. Drug delivery to the target cells by nanomaterial is a point in focus. This process not only reduces the damage to the healthy cell but also declines the drug wastage. The North Carolina State University is trying to develop a process to deliver healthy cardiac stem cells to damaged heart tissues. Researchers at the University of Wisconsin, they have demonstrated a bandage that applies electrical pulse to a wound using electricity produced by nanogenerators owned by the patient. This reduces the long healing time required. Now there are nanotechnologies that are being used in agriculture. At present, we are using nano pesticide, nano fertilizer. This effectively increases the productivity without damaging the soil and water. Silver nanoparticles and silicate nanoparticles, these are used in the packaging and storing of foods, which not only increases the taste but keeps it bacteria free. Even in cosmetics industries, we use nanotechnology. The sunscreen lotions are enriched with titanium dioxide nanoparticles, which enhances the UV protection factor. So, in a very recent work, nickel incorporated diamond-like coating, generally known as DLC thin film, have been developed by scoop-tearing method, and this material shows reversible semiconductor to metallic transition at a moderately low temperature. This DLC offers negligible friction and provides self-lubricating. So, a coating of this material over prosthetics confirms whole life service and need not be replaced. So that we see that nanomaterials and condensed matter physics are highly engaged in our day-to-day life, and its further advancement ultimately defines the new pathways of human race. And I would like some few words about my very previous experience. It was a time when I was postgraduate student at Burdwan University. In our freshers welcome, one of our teachers, very eminent person, was engaged at that time in the sun of Geneva. So he sang a beautiful song that was basically Sama Shongit, and two lines I can remember right now, that তুই যারে ভাবিস ফণি তার মাথায় আছে মণি. So it immediately takes the point that even the poisonous, highly poisonous snake, even that possesses precious gem on it. So that means in every negative situation, we always have some positive outcome. So there is no negativity at all that doesn't come with positivity. So we can also say, in the case of COVID-19 also, this epidemic time, we at Kulti College, it would be very difficult for us to conduct international seminar like this. It is possible to conduct and to obtain speaker like this, eminent scholar, eminent speaker like this, only due to COVID-19 pandemic situation. So lastly, I would like to say thanks to all the participants and all who are hearing, and just enjoy the talks, just enjoy the seminar so far. Okay, over to Atul Nandi. Okay.
Dr. Shah. Now we'll start the technical session. So we have our three eminent speakers with us. So today's first speaker is Professor Arnab Chakraborty. So let me have the pleasure to introduce you. Professor Chakraborty, he did his graduation from Scottish Church College, Kolkata, and master degree in physics from University of Calcutta. He obtained his PhD degree from Saha Institute of Nuclear Physics, Kolkata, and professor chemistry from University of Kolkata. Professor Chakraborty is currently working as a professor, Department of Physics, Basic Institute. More than 30 years of teaching experience. He has lot of academic recognitions within the research area. In 2005-2006, he was a guest scientist at Max Planck Institute for the Physics Complex Systems, Dresden, Germany, 2 times for the Institute. And in 2009, he was a visiting professor of Department of Physics and Astronomy at Uppsala University, Sweden. And in 2009, he was again visiting professor of University of Warwick, and also because acted as deputy scientist in 2013 for 1 month in International Center for Critical Physics. So it's a long list actually, so I have mentioned very few of them. As a researcher, his primary interest is theoretical condensed matter physics with special thrust in the physics of localization and delocalization of excitation in disorder and dynamic factor. Currently, he is also trying to study the spin light concept of quasi-dimensional model system with the emphasis on from origami wave multiplies. We will discuss in a more fundamental way the part of what's the role of geometry, translational order, and beyond. We will talk about from fundamental point of view and obviously so I give this Dr. Chakraborty to deliver your presentation, sir. Please.
Thank you very much, Atanu. Just time to time, let me have your feedback that everything is all right. Thank you all who have assembled here really in this rain-soaked, pandemic-troubled day in August. It's a pleasure to be with you all discussing some of the things that interested me for many years now. And I'm just trying to take a look back at these things, and I can assure you that it's going to be like a storytelling, more like a storytelling, and there is not a single equation in this entire set of slides, and maybe slightly unprofessional in that way, but I prefer to give this talk in this way. So let me just start presenting now. Okay, so I am starting to present. It is visible. I'm just making it full screen now. Visible, fine. So, as you see, the title of the talk was the crystals from origami to a Nobel Prize. So, first, let me assure you that I am not a crystallographer. In fact, crystallography is a subject which always appeared to be very tough to me. Okay. But there is something I'm going to tell you about, which is intimately, or which finally got intimately related to crystallographers all over the world. And then there was a journey that started from that point that is still going on, exploring novelties in condensed matter physics or physics in general that involves even the latest interest of something called topology in condensed matter physics. But I will not go up to that far. I will start with very basic things. Let us focus on certain geometrical shapes, certain regular geometrical shapes that we all are familiar with. And see, so I have written some numbers 3, 4, 5, 8, 7, 6, 10, and 12. These are the numbers of the sides of this geometrical shape. Say a triangle has 3, a square has 4, and a pentagon has 5, and so on. And there is a symbol theta here. Everyone knows what theta is. It is typically used to designate either an angle of rotation or a phase, for example. Here it is an angle of rotation. This meaning of this expression is that with capital N is equal to 3, 4, 5, 6, 7, and till 12, 8, 10, 12. Not all the integers are here, as you can see. That if I fix, for example, I am now pointing my cursor to the triangle, in the middle of the triangle. So if I fix a stick in the middle of this triangle, and the stick points away from the screen of your computer, that is towards you, and if you turn the triangle around that stick by an angle 2 pi over 3, the triangle will map onto itself. Similar thing will happen if you fix a stick here, right, and the stick pointing towards you out of the plane of the computer screen, and you turn the square by an angle 2 pi over 4 radians, which is 90 degrees basically, then the square will be mapped onto itself. It simply means, and this happens for all such geometries with capital U taking these values. The statement implies that if before turning you observe the geometrical shape and close your eyes, and then turn, or somebody turns for you, and you open your eyes, you will not be able to find any difference in the appearance of the geometric shape. This is actually very important for us. Okay, so let us use a term here that we will say that such geometrical objects are capital N fold symmetric, F-O-L-D. So fold means the value of the integer. So this square is a four-fold symmetric object. The pentagon is a five-fold symmetric object. This hexagon is a six-fold symmetric object, and so on. I hope this is clear to all of you. And let us move over to the next slide now. So let us start playing a game. We wish to fill up a plane with such tiles with regular geometry. The tiles I showed you just before, every tile had a regular geometrical shape, and we put a condition that we shall leave no gaps in the design pattern. That is, tiles will just sit side by side without any gap in between. This is our choice, okay? And let us see if we can use a square for that. And so the second square comes, sits like this. And the moment you have this, you see that I have just drawn three. So I have a two-dimensional surface in front of me, and I can safely place squares one after another to fill up completely this two-dimensional plane without leaving any gap. You can see that you can easily place a square here and continue like this. And in principle, if your two-dimensional plane goes up to infinity in either direction, you can continue your game till infinity is reached, which is never reached. So you can completely fill up an infinite two-dimensional plane by such a geometry. The same argument holds if you have structural unit which is a hexagon, and you see that you can easily fit hexagons side by side, and in this gap you can easily slide in this hexagon and put it here, and you will immediately see that it fills nicely. Triangle, okay, it fills nicely, as you can see. Triangles also do the same. Sorry. So this is these are two triangles, and of course you can just tilt a triangle and fill in this space, and you can continue doing this. You see this geometry. You have basically, these are actually, I believe, decadons or more. I will this future, but so now I have a hexagon. So these are, you can take it as spheres even, or circles even. There are many sides here. It's a polygon, but you can join the centers of the polygons like this straight line. So essentially, the centers lie on the perimeter of a hexagon, and as from this figure, you know that the hexagons really can fill up the space. And here is just another showpiece to show that definitely triangles, they can be adjusted in many ways, and it's quite interesting to see that here you can identify inverted triangles as well, but you can also identify this kind of structure, which is nothing but a hexagon. So 1, 2, 3, 4, 5, 6 triangles are packed inside a hexagon in a rather symmetric way. And if you have an infinite geometry and you fix a stick right at the point where the cursor is pointing, and the stick points away from the plane of the computer screen, and if you turn the whole infinite geometry by an angle of 2.06 radians, the whole geometry will get back onto the hexagon. So you see this four-fold or three-fold or six-fold symmetric objects. They are very nice objects to tile up a plane completely when placed side by side so that no gaps occurs. Now let us try to do the same with a pentagon, with a regular pentagon. The moment I try to do this, we immediately see that there is a question mark that I have put in here, and there is a narrow gap. And it is very simple to argue in your mind that you can never push a pentagon inside to fill in this gap. This, you call it frustration. Okay, your geometry gets frustrated. You cannot do anything else. Anything here using the same pentagon. I have just tried to increase the generation of this, and the moment I do this second picture is rather interesting. The third one is too intricate too complicated to follow. But the second one is interesting in the sense, okay, I will be speaking about this later as well. But here you can see that if you really put some colors inside, this is the pentagon, that is a pentagon, there are two pentagons here in this cluster, and in between there is something like a Kaju Burfi. And so if you were allowed to pick up an extra geometry, which is a rhombus, a thin rhombus like a Kaju Burfi, in principle you could paste it here, right? So if you consider these burfis as your assistants in tiling up a plane, you can argue, okay, I can have a plane tiled up using at least two kinds of such geometries. Fine, I do not object to that. But my initial discussion began with the possibility of tiling up a plane using a single geometry which has a regular geometric shape. You see, the same kind of frustration occurs when you try to pack octagons in a two-dimensional plane. You immediately generate voids in the geometry which no other octagon can fit in. But you can fit in a pentagon on one side of an octagon, this Sudarshan Chakra-like figure. This can of course be there, but the notes of interrogation will be there, okay? Of course, as I said, you can have a pentagon decagon unit. See, individually, the failure that we saw using pentagons will also occur if you try with decagons. But if you are allowed to use more than one such geometries, so using a pentagon and a decagon, you can definitely tile up a plane. And the important thing is that the design does not seem to be random. It's not something that you cannot predict. In fact, this packing has a definite pattern, that the pattern that you have designed to fill up a plane using these two structural units. So apparently so far we have been concerned about tilings. We will be concerned about tilings almost always. And these really look nice if anyone thinks of designing these or half apartment floors. These are very strong colors. I know Amrita is listening to me, and Amrita will object to using such very strong colors. So, but never mind. And so these are examples where you can in principle have multiple units, as I was telling. If someone allows or someone takes off the restriction that, okay, I take off the restriction of using only one kind of object, and you are allowed to use as many objects as you can, but all objects need to be regular geometric objects, then of course we have a wide set of possibilities. And here are some designs like hexagon and triangle coming together, joining hands and tiling up a plane. And here we have squares and hexagons and triangles. They can do wonders. So these are very lovely pictures. And I think everybody should be very happy seeing these colorful objects. But the issue is, we cannot do this again. I'm coming back and hammering on the same point, that we cannot do this by using a single pentagon, a single octagon, or a single decagon. Okay? Very nice. What is the other option? You can go for a completely random tiles. That is, you can pick up geometrical shapes. This is what origami is all about. You can cut pieces of papers in all possible shapes. And in principle, if you have a very wide choice of slabs lying in front of you, slabs having any kind of geometrical shapes, that is in totally random fashion, they're scattered in front of you, then you can pick up, this is actually a portion of a wall, and you can see that somebody has used slabs of all possible shapes to tile up this wall very nicely. And there are some cracks here and there, but you can always pack some sand or some grains here. They will just form a part of the random packing of the system. And this is an origami which is done using random geometries. While using random things, you can of course tile anything. But this is not our concern here. We are not bothered about randomness here at all. rather we are bothered about some strange kind of ordering that we are going to learn in a few moments. So let's get back to the ordered regular shapes again. So square is something which we accept because it can tile a plane without leaving any gap. It has a fourfold symmetry. So 2 pi by 5 is the value of theta, the value of rotation about an axis at the center of the sphere. And then you can have another cell which is a hexagon, and it has a 6-fold symmetry. And then of course you have the triangle which has a 3-fold symmetry. We shall call these structures our good unit cells. Why unit cells? Because taking them as structural units, we can tile up a plane just by shifting one tile after another in any direction. Okay, and what is the frowning smiley here? It's frowning at the two structural units that are not our choices. One is pentagon, another is an octagon. Of course, decagon and septagon and everything is there, but I am not mentioning all these structures. So the structures belonging to this class, which cannot tile up the plane without leaving any gap, we will call them bad unit cells. Okay, so we have bad unit cells, we have good unit cells, and the summary is that only certain rotational symmetries are allowed when one talks of space theory. So this is a point that is normally taught in undergraduate solid state physics course at the very beginning, though we have not mentioned anything about solid state physics. In fact, this discussion is quite general, and you will see in a moment that this kind of interest was generated in human society since ancient times. Okay? So in solid state physics was not discovered by them. But just from simple geometric arguments, we can see that filling of space is associated only with certain regular geometric objects which has special rotational symmetries. So if you call these 4-fold, 6-fold, 3-fold rotations as allowed rotations, of course 5-fold, 8-fold, 10-fold or 7-fold or 12-fold, these will be disallowed rotations. Disallowed in terms of what? In terms of using them as space-filling objects without leaving any gap. Right. So I have to introduce two technical terms. So this is basically a patch of a rectangle, or I have scooped it out from an infinite square geometry where you can see that these blue squares are there. I have marked one square by red. And suppose, as you can see, suppose all these squares except the first one were empty at this moment. Then what you can do, you can replicate this square one by one and generate this row. And then you can replicate this whole row and shift it in the downward direction or the upward direction to generate this kind of beautiful square geometry. Okay, so this we are just shifting the square by one unit. This is what is meant by a translation. Okay, so we are translating one square in X direction and in Y direction to generate this whole pattern. Suppose this red line, which I have just encircled with this golden color, this red line stands for some kind of bond. This is a talk that will be valid for physicists, for mathematicians, for chemists, and for artists as well. So bond is a general term. So suppose someone is here and someone is there, and this bond is tying these two units up. So if you see this is a bond here, then immediately you see that you will be getting another bond and another, which will be parallel to this bond. And if you just extend this diagram mentally, and you will immediately find that just if you fix your origin somewhere here, no matter how far you travel in X or Y, you are always going to get at least one bond that will be parallel to the bond at your hand. This is called long range. Apparently it is long range. This is called the bond orientational order. Actually, this comes very close comes as a result of this long-range translational order. And there is a subtle meaning of translation as well. And you see that suppose some observer was sitting here and he was looking at this entire geometry, and then I close the eyes of the observer and I translate the observer from this point to that point. That means I traverse 2 units here and 1 unit there. So 2 X translations and 1 Y translation, and the observer sits here, and then I open the observer's eyes, and the observer will not be able to find any difference in its environment. It will look exactly the same. So this can happen no matter how long this green arrow is. Okay, you can take the observer from here to eternity, and still when he opens his eyes, he will not be able to see any difference in his surroundings from what he saw before. So this is what is meant by long-range translation. So, and you see that, of course, this is related to what kind of regular objects you are using to time them. Okay? So, long-range translational order and bond orientational order, they actually shake hands with certain allowed rotational symmetries, which are, let me remind you again, 3-fold, 4-fold, 6-fold symmetries, and nothing beyond that. So what about 3 dimensions? Because we live in a 3-dimensional world, and you can immediately see that a cube is basically a 2-dimensional version of a square, and you can easily stack one cube above the other, or just side by side to fill up a 3-dimensional space. There will be no gap. It is very easy to conceive of. And this lower figure is a slightly more complicated geometry, which many of you must know. It's called a buckyball. It's the model.
Sorry for interruption.
Yeah.
Sir, please share your screen once again. Someone shared screen.
Okay.
Your screen is not shared.
Okay. So I'm resuming my presentation. Okay.
Yes. Yes, now it is coming.
It's okay.
Yes, make it full screen, sir.
Yes, of course. Is okay?
Yes, yes,
Yeah,
yes,
yeah. Okay, so this is called, this is a model of something called a C60, carbon-60 molecule, which is popularly known as a buckyball. And just on this face, you can see a hexagon. Okay, carbon loves hexagons actually. So this is also an example of a space-filling structure. But our interest begins with the observation that there are some knotty elements in 3 dimensions, which actually, though themselves they are very regular in appearance, they are reluctant to fill space in a dense possible way. So I have just picked up 2 examples, 2 very famous geometries. One is called an icosahedron like this. You see every face, there are 20 faces, 12 vertices and 30 sides. And every, Otome, just can you give me a warning 5 minutes before I need to stop? Okay. So,
yes, sir.
yeah. So every face is basically an equilateral triangle. And if you try to back such shapes side by side, you will immediately see that frustration will develop in the sense that you will get a point in which no other icosahedron can come in and sit nicely. And the same happens if you use something called a dodecahedron. I can assure you that geometries have been known to mathematicians for.
Sir, we cannot hear you.
Is that so? Now, what happens now? Sorry,
Sir, it's not audible.
it's not audible.
No, sir.
Is it audible now?
No, no, no. Very, very faint.
Just a moment. Let me see what I can do. Is it better now?
No, no, sir.
Oh my God. What I can do, I can just. It's still not audible, right?
No, sir. Still now not audible.
Okay, then I need to switch over to Linux. Can you spare me 5 minutes? Because I need to switch on to Linux. That will work again. Or I'm not sure what is happening here. I am not sure what is happening here.
Okay, sir. Please sign out and then rejoin again. I think that will solve the problem.
Yeah, so I'm signing out and rejoining, okay?
Yes, yes.
Is it okay, Apollo? Hello? Hello? Hello?
Sir, have you joined?
Yes, I have.
Sir, can you hear me?
Yes, he has joined. He has joined. He has joined.
Sir, can you hear me?
But he is not audible. He is not audible. Atul. I have pinned him also, but he is not audible.
Uh, হ্যাঁ স্যার শোনা যাচ্ছে না তো
So can you give me 5 minutes? I want to get out of this and get to Linux.
ওকে ওকে স্যার ওকে
Just give me 5 minutes.
ওকে 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 So participants, please have patience. Some technical problem occurred, so sir will rejoin again just for 5 minutes. Participants, please wait just for a few minutes. He will again join, please.
Participants are requested to put off their video. Okay, please put off your video. পুয়ার কানেকশন আমার দোষ নয়। এত তখন আমি আসেনি, আমি হচ্ছে গন্ডগোল হয়েছে, আমি গন্ডগোল হয়েছে, আমি কেটে দিয়েছি, ভুল করে এন্ড করে দিয়েছি।
Participants, please do not share your screen. Don't switch off your video and audio. তুমি কস্তুরী দেবকে রিমুভ করো এই মুহূর্তে। কস্তুরী দেবকে রিমুভ করো পার্টিসিপেন্ট লিস্ট থেকে, বারবার শেয়ার করছে।
I have joined. Can everybody hear me now?
Yes, sir.
Hello?
Yes, sir, we can.
Yes, sir, it is audible.
Yes, sir.
Well, it's audible. Okay. So I'm getting back to the. I'm sorry for this. I'm just getting back to the presentation, and yeah. So just let me know when you see this. View full screen. Yeah, we are
Yes, sir.
again just. Okay. Okay. Just a moment. I don't like this font. I will just do it again. Yeah, this is fine. Okay, this will be fine. So this will be fine. I hope you can see it now again, right?
Yes, sir. Yes, sir.
Okay, so I am continuing from just where I left. I believe I was here. So this was perhaps the area where I was squeezed out of the meeting. So icosahedron and dodecahedron in 3 dimensions, these are the bad elements that we should be careful about. They individually they look very beautiful actually. And there is a huge subject called group theory that deals with the symmetries and their effects and all these things. But these are not good for our kind of purpose. Okay, that is space filling. So see, so I got rid of the animations. So division, as I was telling you, division of a plane into regular polygons. Tiling means if you see it the other way, that is, you can have a plane which is already tiled, and then you can isolate the polygons that are placed there of that tiling. This is an ancient game. For example, you see this is the geometry in a mosque, and this is a mosque that was in 1453 in Isfahan. And just look at the geometries, you see. And some mathematician, he has taken great care in separating out certain regular geometric shapes that we are familiar with. These are actually parts of the geometrical shape. And you can easily see rhombus kind of stuff here. And the angles, startling, as you will find in my later slides, that angle is something to do with something more serious. But I can assure you that at 1453, nobody really bothered about other serious consequences coming out of such geometrical objects. It was kind of a challenge for them, a kind of an interest, kind of a game to tile up planes using different kinds of such samples or such tiles. But you know, science cannot proceed in this way, so one needs to have a rigorous kind of theory to look into such objects. And the first rigorous mathematical treatment of tessellation means tiling of this plane. It came from Johannes Kepler, lived from 1571 till 1630. And so this was a man who is known for his laws for discovering planetary motion, identifying them, chalking out the design of the planetary orbits and doing all kinds of intricate calculations. And Kepler in 1619 wrote a book. It's a 5-volume book actually, Harmonice Mundi, which means the harmony of life, or harmony of the world, I believe. So it's a mathematical, basically it is a mathematical description of the planetary motion in heliocentric systems. And while studying the orbits of the planets around the sun and the geometries of the orbits, Kepler got interested in joining the instantaneous positions of the planets using lines, and then he discovered that he was basically drawing certain polygons in space, and from that somehow his interest for certain days or maybe a year or two shifted towards designing polygons much in the spirit of an origami, which could in principle tile up a two-dimensional plane. So these are some of the geometries Kepler worked out. You can see that this blue is once again a regular pentagon, and then you have some pentagons fitted up in this pattern. And if you really wish to fill up something, you have to have a star of these number of sides. Okay, and here is another example where pentagons and stars and those Kaju burfis, they sit tight together to tile up a plane. So Kepler continued this work actually, but I can assure you that once he identified a basic structural unit, he had to repeat that structural units in a completely periodic manner, placing one by the side of the other in either direction, in all the directions rather, to tile up a plane completely. Okay, so these are only local tilings. But you have to mentally extend such local tilings to see the effect on real two-dimensional plane. And as I told, that this talk is also related to artists, and one such artist, famous of his own kind, was Michel Escher, is a Dutch painter who started filling up a canvas using weird kind of animals and shapes, and you see that this is completely space filling, right? And follow the cursor. If I go along this direction, essentially this is a periodic array of fish and a swan in an alternating way. But now the second row is kind of shifted with respect to the first, and this goes on and on, goes on and on and on. So in this direction, if you follow the cursor now, it's fish and fish and fish and fish and fish and swan and swan and swan and swan and swan. So it's a strange kind of periodic order that Escher painted here. And now here you have swans curling into one another. The point behind showing these slides is that this is a pattern which you really is very difficult. This particular one is very difficult to find the exact regular periodic pattern of drawing such things. It's almost impossible here. At the same time, as you can appreciate, that it cannot be completely random stuff. Had it been random, then Escher would have failed at least at one place where he could not fit a swan. So there must have been some rule. That rule I do not know. Escher definitely knew. But this was his passion. So this comes, Escher was not a mathematician in that way, but he has very strange mathematical models depicted in his drawings. Okay. One such famous picture is called a devil's staircase, where you just keep on climbing on and on and on and never reach the top. So the issue is, this is our central issue. We can now try to connect with physics in the remaining part of the talk. And of course, we are not ruling out mathematics and chemistry. So let us try to look for a geometry in between a perfect periodic order and a completely random disorder. It's something like this. Okay, in Bengali, we call it something like a shonar pathor, something like that. Okay, the stone ball of gold, something. I am a very bad translator in these issues. So if that is possible, then we would like to call it an almost periodic order. And this is the Latin for almost, so it is quasi-periodic order. So something which is not perfectly periodic, like a soldier is taking periodic steps, every step is say 1 foot away from the other, and a drunkard, he is taking a completely random sequence of steps. But we are looking something in between which cannot be called a soldier-like periodic stepping in terms of space filling, of course, and the completely random steppings of a drunkard. Okay, so we are trying to look for this. Actually, people look for it, And the most famous people now in history of mathematics, the living legend, is Roger Penrose in Oxford. He should be around 90 now, I believe. He finds an answer. He finds that, okay, we can have four basic shapes. So pentagon, regular pentagon, the regular thin diamond, this angle is 36 degrees. A boat shape, which is also a very regular shape. He just made it by cutting papers, okay? And this is a star. And then he says, okay, if I fit these objects in this way or that way, you see that any void that appears in between, the void can be filled up by at least one shape that is here, okay? So he doesn't have to go beyond the set of these four objects. So these can be examples of his basic structures. And then when he joins it using pieces of paper, he designs something of this kind. Okay? Now, have a close look at this. Have a close look at this. You see once again that this cannot be a random design. If someone is drunk completely, he can never design it this way, because if you forget to use the proper rules of fixing a boat with a pentagon, immediately you will land up with a gap that you can never fill up in your life. Okay? So everything will be destroyed. And please remember, you are given four basic objects and you have to fill in any void appearing anywhere using only one of those four objects. So you can guess that there must be some fitting rules. At the same time, you begin your journey anywhere on this slide and try to find out a single structural unit that is periodically repeated in any direction to generate this figure, you will fail. It is not like the square tiling or a triangular tiling or a hexagonal tiling of a plane. You cannot find any single structural unit. That is, you cannot find a long-range translational order, okay? But you take any side of any pentagon, say this is the side. Immediately you see that if you go to this side is parallel to this side, right? And then you travel and find this side, which is parallel to both these. And this will happen for all pentagons, all stars and everything. That means you now have landed up with a geometry where you do not see any long-range translational order, but definitely you see a long-range bond orientational order. Okay? There is now a conflict of concepts here. And not only that, let me tell you, if I could just expand it, say the central flower, if you fix a stick here and point it towards you, away from the plane of the computer screen, then if you turn the whole figure by 2 pi by 5 radians, the whole figure is going to get mapped onto itself. So what is the lesson? What is the take-home message here? Now, the take-home message is we are in a soup. We have encountered a very strange kind of geometry because you know, pentagon, center of the pentagon, fixing a stick, turning by 2 pi by 5 means you are talking about a 5-fold rotation given to the whole system. Now, 5-fold rotation does not go with space filling. It does not go with long-range translational order. Fine. It also does not go with bond orientational order. Here comes the conflict. You are having long-range bond orientational order and you are having 5-fold rotational symmetry of a geometry. So this is a geometry which Penrose called a quasi-periodic geometry. So this is the first kind of example where you see quasi-periodic order in origami. So suppose we wish to do really an apartment where my floor will be tiled like this. But the problem is now we have too many tiles. 4 is actually too many. And when 4, the number 4 itself may not be a very large number. But when you try to fit in with the fitting rules, with the fixing rules, then it becomes very, 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 very complicated. So the next issue was, can we really reduce, or could Penrose reduce the number of tiles? And the answer was yes. He finally discovered that the tiling could be done using only two rhombi. One is a thin rhombus having an acute angle of 36 degrees. Another one is a fat rhombus having an acute angle of 72 degrees. And then he discovered a joining rule for them. And this is one basic flower that comes out of such joining. You can immediately see if you go by the outermost perimeter, it is a decagon.
One more introduction, please.
Yes?
Sir, please share your screen again. Come on.
Oops. Okay. Okay.
What is
So I am resuming presentation, okay? Is it okay now?
Yes, sir, it is okay.
Okay. So you see, if you traverse along the outermost perimeter, it's a decagon, right? And this is the point, which is a five-fold symmetric point. That means once again fixing the stick story. You put a stick here away from the plane of the computer screen and turn this flower, his football, by 2 pi by 5 radians. The football gets mapped onto itself. And when Penrose expanded this on a two-dimensional plane, here is the geometry. Here is the geometry using only two kinds of rhombi. The dark blue is the fat one, the sky blue is the thin one, and this cursor points at the center of a five-fold flower, around which, if you turn the entire infinite geometry, please mind the word infinite geometry by 2 pi by 5 radians, the geometry comes back onto itself. And here is a split showing what is there in the rhombus. And there's a beautiful story here. If you take the length of this side and divide it by the length of this side, this smaller side, the ratio turns out to be square root of 5 plus 1 by 2, which is called a golden ratio. I will show you a couple of slides on that as well. And so this is Roger Penrose standing, smiling and happily on his own tiles, okay, in Oxford. And of course, as you can understand, mathematics is not confined to textbooks. This is a picture from Netherlands, public place where people can sit on Penrose tiles really and enjoy a cup of ice cream or so. And we are back to Penrose tiles. This is a hand-drawn Penrose tile. So the green ones are the basic ones, and the red ones are some kind of inflated tiles. Now, suppose I pick up anyone from you who has an eyesight such a way that he or she can see only the green ones. So the observer's conclusion is, okay, there is a Penrose tiling pattern lying in front of me, and then what I do, I draw larger Penrose tiles using bold, thick red colors like this. And I just did not continue. I could have continued. And you can visualize that if I could do it on an infinite kind of geometry, then I could have generated the same design, but now with some larger tiles, larger red tiles. And now if I give someone a pair of glasses so that he or she can only see the red ones, the second observer will shout, okay, I am also seeing a Penrose tiling pattern, but my tiles are actually bigger in size, but the angles do not change. That is very important. The angles do not change. So actually the two observers are observing the same tiling pattern at two different scales of length. This is a very important terminology. And so this is called self-similarity, okay? You observe a certain object at different scales of length and you basically look at the same geometry. You say the object is self-similar. So these are the special features of Penrose tiling pattern. So they exhibit self-similarity. Although how much time do I still have? Just can you tell me? I can sort of...
Yes, sir. Take 15 minutes. You can go.
Fine. Okay, so Penrose tiles, they exhibit self-similarity. Penrose tiles exhibit long-range bond orientational order, which I just explained. And most importantly, with an infinite Penrose tile, if you really could count, there is a way to count, let me assure you, that the number of fat rhombi to the number of thin rhombi, this ratio is going to give you this famous number, which is called the golden ratio. this number was known to mathematicians all over the world thousands of years before Penrose was born. Okay, from very, very ancient times in Babylon, in other places of Egypt, in Greece, and everywhere. And this is called a golden ratio because of this. Just a couple of slides, because our golden ratio itself can take a full talk. So this is like this. If we take a line, okay, so this segment is A and this segment is of length B, and this total is A plus B. So if you divide this full length A plus B by A, that will be the same as A divided by B. It is always, it's 1.618 dot 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 dot, which is square root of 1 plus 5 by 2. This is like the square is a rectangle. You split the rectangle in a golden ratio so that this side divided by this side is once again golden ratio. This full side divided by this side is again golden ratio. And this ratio is golden because it appears in arts, mathematics, geometry, beauty. Don't frown, it's in beauty, as you will see, in design, cosmology, theology. This is about religion and life. So the pyramids, you will find golden ratio and certain, if you just split the side and take a ratio with half the height to half the side or something like that, you will find that this number is appearing here. Take a violin. So these are the segments which are in golden ratio with each other. And this is beauty, nobody will deny. This is a Mona Lisa face. This length divided by this length is golden ratio. And Leonardo da Vinci was perfectly aware of this ratio, and at that time, somehow they knew that if you draw something with golden ratio coming in the proportions, then the picture becomes very nice looking actually. Okay, very symmetric, very nice looking. So, and here is the famous temple of Parthenon in Greece. And all these red lines, they share golden ratio in between them in the way it's shown here. And you take the palm of your hand, you will see this full length divided by this length is golden ratio. This length divided by this length is golden ratio. Take your hand, this shoulder to the tip of the palm, divided by the elbow to the tip of the palm. You will get approximately, of course, golden ratio. This is drawn for the perfect human shape. And the flowers, they often have, very frequently they have petals in numbers 5, 8 or 13. All these numbers, 1, 2, 3, 5, 8, 13, these are called Fibonacci numbers. And if you take, for example, 8 Fibonacci number and divide it by the earlier Fibonacci number 5, you are close to golden ratio. And this goes on in the sequence. And then this is the Cathedral of Notre Dame. And you will find the golden ratios here. You can now figure out what I meant when I drew lines over here. And some galaxy spiraling technique and the snails, Shalagram Shila we call it. So you will find golden ratio here. Okay, but this is not the central issue of our talk, so we'll just skip this slide quickly. And just don't get scared away for the rest remaining 8-9 minutes. So, now suppose we know now about Penrose tiling and we wish to link such geometries with physics. Now you know, those of you who have read a little bit of solid state physics, that we have something called a lattice, which is basically a cage. Okay, and the entire crystal structure is based on a description of such lattices. And the lattices are normally in 2 dimensions, made of square or triangle or hexagons. Okay, and definitely not pentagons, because they cannot fill space. So a square lattice, a triangular lattice, a hexagonal lattice. So they represent perfect crystal structures. So really, if you wish to have a Penrose tiling pattern lying on the screen, and if you think that Penrose pattern is a lattice, what kind of solid will it represent? There were 2 famous results. The first one was a completely theoretical paper, 1983, Levy and Steiner. They proposed that if you choose the Penrose pattern as a lattice, then the solid that will form on this lattice will have to be called something called a quasi-crystal. You see, it cannot be called an amorphous crystal, amorphous system, because amorphous basically means randomness, and Penrose pattern is by no means random. So it's almost periodic crystal. And remarkably, in the same year, in the same journal, just when the paper written by Levine and Steinhardt ended at page 1870 of Physical Review Letters in this year, from 1873, an experimental result came up from Danny Schechtman and his group, who were actually developing some kind of alloy made of aluminum and manganese. And they prepared the alloy. They did electron diffraction and X-ray diffraction experiments on that, because X-ray is a typical tool, as the departmental head mentioned, that it's a very old and ancient tool for exploring the crystal structure. And surprisingly, they observed 5-fold and 8-fold rotational symmetries in the crystals. So they say, okay, this is a typical, if anybody forgets what a diffraction is, this is something you send a light through a blade, you will be seeing these patterns. And this is how you learn Bragg's law in your textbook. And the diffraction pattern comes from some glassy structure. So these are interference patterns. So this is what X-ray crystal from a regular, X-ray diffraction from a regular crystal looks like. You see, I could draw squares, right? So the points, the bright points, they're sitting right on the vertices of squares. Now, brightness means the amplitudes have made a constructive interference there. More amplitude you have, more bright is the spot. And how can you have more brightness in your X-ray pattern? It means you have many, many lattice planes lying parallel to each other over a long, long distance. That is, brightness is a signature of a long-range translational order in your system. And if you turn this whole figure around this point by 2 pi by 4, this entire X-ray pattern will come back onto itself. So it's a 4-fold symmetric pattern. So it comes from a crystal which is a 4-fold symmetry axis. And if you do a mathematical calculation using the Penrose tiling, suppose a scatterer sits at every vertex, and there is something called a Fourier transform technique, which tells you what will be the diffracted pattern when you send a beam, when you send a beam through this structure and observe a calculated diffraction pattern. The diffraction pattern looks like this. First, see that there are bright spots. That means there is a long-range order. Then you see that these bright spots are joined by pentagons. And this is a central bright spot, which we call undiffracted beam. Okay. Now you fix your stick here again and turn the geometry by 2 pi by 5. All the bright spots will get mapped onto themselves. And you see I have drawn certain pentagons. You take a side of this pink pentagon and divide it by the yellow side. The ratio will be golden ratio. You take this side, divide it by green, the ratio will be golden ratio. So there is strangeness here again. And this is the actual quasi-crystal pattern that was observed by Schechtman. And you see, it's the same pentagons here, and no need to say that you will again be getting the golden ratio if you divide one side by the other. So brightness of the spots, scales of long-range order, but at the same time, you have 5-fold symmetry axis. So this is our Sonar Papurbahi. You have a long-range order, which never any crystallographer ever thought of having in their crystal structure, because long-range order could not go hand in hand with the 5-fold symmetry. But now you have that. So definitely it is something which is a third-order phase of solid, and that is quasi-crystal. And so there are many applications, wear resistance coating, non-stick coating, polymer materials. They paint things with quasi-crystalline systems or alloys on the aeroplane wings and all these things. But the important thing is that this discovery was made by a man who was actually thrown out from the community because he tried to prove something which crystallographers did not believe till that day. And he was Danny Schechtman, who finally, after a long battling career, won his Nobel Prize in chemistry. And this is the aluminum manganese alloy, which is a dodecahedral quasi-crystal, you can see that you have a clear pentagon sitting on one side, and this was the picture I showed you earlier. So this was Shechtman's story, and from origami we have reached to the Nobel Prize. And just to conclude, the story doesn't end here, because the concept of quasi-periodicity goes much, much beyond the field of crystallography. Now the International Union of Crystallography has classified solids into periodic crystals, quasi-periodic crystals, and amorphous solids, not two as it was before. Okay? But the impact is far-reaching, and it goes beyond crystallography, and people using state-of-the-art technique, they are developing artificial lattices in which, using something called cold atoms like cesium or rubidium at extremely low temperatures, the atoms get some kind of trapped in potential wells, and the potential profile takes a quasi-periodically varying mathematical functions shape. Okay, and that results in remarkable pictures of band structure. It leads to something called an understanding of a very deep subject called Anderson localization, and finally topology as well. So I think that will be a very large section to talk about again. And I thank you very much for your very patient hearing, and I apologize for any interruption caused by my own systems. Thank you very much.
Thank you, sir, for your illuminating talk. So we will now go to the question answer session. So can I go for it, sir?
Yes, please.
So there are 3 questions from the participants. First question is, can any structure other than penetrine give rise to other some ratios?
Yes, this is an obvious question, and I can assure you that there are hundreds of such structures. Mathematicians have worked out many structures. Only thing we have to be careful that if you really try to develop a structure of your own, you can succeed for up to certain distance or certain area coverage, but you have to ensure that it is quasi-periodic, because quasi-periodicity has a very severe mathematical definition. Okay, so but people have done this. There are many variations in 1 dimension, in 2 dimensions, in 3 dimensions.
So, sir, second question is, for quasi-crystal, 5-fold symmetry exists, but why not in ordinary crystal?
Oh, that I explained actually, because ordinary crystal is very much restricted with the concept of space filling. Okay, and space filling is by regular geometric objects, which is forbidden. Okay, I mean, as a pentagon is a forbidden structure, a decagon is a forbidden structure. So you really cannot think of an ordinary crystal lattice having a pentagon or a decagon or a septagon sitting as a structural unit there. Okay, so that is the problem. We will have voids which will prevent any translational order, long-range translational order, which is essential for a regular crystallization.
Okay. Sir, next question is, can you comment on the advantage of quasi-crystal?
Okay. As such, I showed you some applications. Okay, so I will not say that those are all the applications. There is no as such advantage. It is a new material. The first impact that I would like to point out is that this is a tremendously important and new symmetry that people could never think of. And now all those paintings, coatings, quasi-crystal is generally a ductile kind of material. So people developed even frying pans where you could put a quasi-crystal coating, so that you could even use a non-stick frying pan where you could use steel cutlery. Okay, but I'm not sure whether frying an omelette is a very big advantage for any one of you. But there are many applications. In Sweden, they have a very big steel factory who mix quasi-crystals with steels to give it more stability, more ductility, and it's used all over the world. We don't know of all the uses. Of course, it doesn't come out every day in Anandabajar Patrika, so people do not know about it. But it has its own use. Otherwise, if you think of electrical conductivity or thermal conductivity, as such, these are poor conductors of electricity and heat. Okay, so at certain point, if you are not specialist enough, it will be difficult for you to differentiate it from an insulating material. And nowadays, in my last slide, which I did not talk about really, I wish I could, these potentials really, the potential profile, which would be a quasi-periodic profile, can really be developed using something called an optical lattice, where people use cold atoms and laser beams and all these things. And those things are giving us a wonderful physics. And so far, it is restricted to fundamental physics, but let us, nobody knows where application comes.
Okay, sir. Thank you. So, on behalf of the organizing committee, we sincerely thank you again for sharing some of your valuable time with us.
Thank you for asking me to give this talk.
Yes. So we hope that your interesting presentation will definitely motivate young students, especially, and we are very much fortunate to have you with us. Thank you, sir.
Thank you.
So, our next speaker, Professor Devnarayan Jana, Professor, Department of Physics, University of Calcutta. So, I will give first his formal introduction. He did his graduation from Narendrapur Ramakrishna Mission Residential College under University of Calcutta. And then he did his master's from University of Calcutta and PhD from Raman Research Institute, Bangalore, and awarded by Jawaharlal Nehru University, New Delhi. His research interest is mainly condensed matter physics, both theory and experiment, universal diamagnetism, mode conductivity, defect dynamics in zinc oxide and other systems, density functional theory in carbon nanotubes, interface growth dynamics in random porous media, nonlinear conduction in disordered systems, DFT study in graphene and silicon, etc. He has also received a lot of academic recognitions. To name a few, he got bronze medal for poster presentation in Taiwan. He was a visiting research fellow, Center for Condensed Matter Science, National Taiwan University, Taiwan in 2003 and 4. And he was also elected as a fellow of West Bengal Academy of Science and Technology in 2015. So today he will talk about Dirac materials. So I request Professor Jana to deliver his lecture. Sir, it's over to you. Sir, can you
hear me? Can you hear me?
Yes,
Okay.
yes, audible, sir.
Okay. So let me. So there is some problem. Let me start. Can you see it? Hello?
No,
Can
sir.
you see it?
Still now it's
Oh, okay, okay.
not.
Okay, just a minute. There is some problem, I don't know. No.
Yes, sir. It's coming.
Yeah, it's taking time. I think there is some problem, but let's start that.
Yes, sir. Can you make it full screen, please?
Is it coming?
No, it has left.
Oh, okay, let me try again. So is it okay? Hello?
Yes, yes, coming. Yes, it is coming.
Okay.
Yes, sir.
Okay. So thank you, Dr. Abunu Nandi, for inviting me to these presentations. And today I'll be talking about a two-dimensional new material or the Dirac material, which is an emerging field of research in last few years. And I am just starting my journey into this new area after working in density functional theory in different two-dimensional material. And so I try to share my effort understanding till date to this new field of area. And hopefully you will at the end will be able to get some kind of message in this journey towards this Dirac material. So mostly this Dirac material presentation I will be talking about the theoretical study on this particular system and their electronic properties mostly will be attacked and how can you do these things. So there are different techniques which will be told as we go on. So I have a planning of these presentations. Mainly I talk about giving a brief introduction to Dirac materials. Then I'll talk about the tight binding calculations, which is the simplest pristine type of calculation in this Dirac material, and you know that it was given a Nobel Prize in 2010. So, and then I'll slightly move to another kind of allotrope of graphene that is called tetragonal graphene, which does not share the same hexagonal symmetry as was told by our previous speaker. So, whether this hexagonal symmetry is a prerequisite for observations of Dirac material or not, we try to look at it. And I will also share some of the possible applications, again theoretical problem, which was actually synthesized in the 2019. Okay, and then I'll go to another kind of system, tetragonal graphene, and try to see some of the features associated with Dirac material number, which is in a nutshell my planning. So let's see how we go. So we start with this famous question which was raised by Professor Bose to Dirac. So what are you working on, Mr. Dirac? So Dirac replied quickly, I am trying to take the square root of something. So something is one. So this is basically an energy, or what we take this px square plus py square plus n square. I am taking in 2 dimensions, and if you would like to take the square root, naturally, as we know already, that it boils down to a linear combination of 2 dimensional power matrix, and in the 4-dimensional community that we will see in Dirac solution, this will be 4 cross 4 matrix. So this is the only technique where you can actually remove this thing, making this contact to be very fruitful to the geometry. And at least we will try to show that can we write down the so-called band structure of a particular material in this particular form or not. Then we can see that this band structure will be linear in momentum rather than the normally seeing that square of the momentum. So let's start this journey, and see in sort of graphite, it has layers with kind of interacting with van der Waals interactions, then to make a sheet of this thing with the appropriate A1A2, bond length 1.42 angstrom, and these are the 2 famous persons, Kim and Novoselov. They are awarded the Nobel Prize of this thing. And here is this first for the Dirac code, where this are touched at only one particular point. So that's why this is called semi-metal, not like the pure metal. And this is the Brillouin structure, and this is just a cartoon picture of applications of graphene to various kind of things. Okay, so let's start with our journey with the simplest electronic properties of materials and actually try to classify the material in three categories mainly: insulators, conductors, and semiconductors. So this is the y-axis is energy, and the x-axis is the k vector. So these are actually gapped by a kind of quantity, valence band, and conduction band. But in the conductors, they do overlap, and semiconductors, the gap is very small. So there are also wide band semiconductors like zinc oxide and other. So there is not kind of a simplest rule which can actually separate these semiconductors and insulators. Okay, so what are these Dirac materials? So say, let me start with a formal definition, then we'll try to cut it short. So these are basically a complex and functional nanomaterial. Functional means it can work in different functions, and it can be used one kind of material in different purpose. So that's why it's called functional nanomaterials. Nanomaterials in the size are precisely between 1 to 100 nanometers, and this has a few points where these changes can happen in the response of the material. As I just point out, this is the Dirac point, which I try to calculate and show you the features. So any material which has this Dirac point and the dispersion is linear, it can be called a Dirac material. Of course, we'll try to see that how can you control the electronic property, so-called the Dirac permeance on this particular point. So what are the major characteristics of Dirac material? So you know that normal metals like gold and silver, they are good conductors. Their band structures are proportional to pitch pair. But the key aspect which can separate the quality of conduction in the way energy depends on the momentum. So as I told you that this Dirac material case, this energy is proportional to P. So linearity has some problem and some advantage. We'll see that thing. So this is the formal definition. And the charge carriers also can have effective mass, because given the linear dispersion relation, so you are in a little bit trouble to how to calculate the effective mass, because effective mass is a quantity which is related to the second derivative of the band structure, which is related to the fluid width. So how to calculate all these things? So we'll try to look out as we go on. So as I have told you, this is the typical low energy electronic structure of graphene. So their mass is 0, speed of light is the Fermi velocity, and we have two kinds of lattices here. There is A types of lattice and B types of lattice, so they are not equivalent. So as you know, this your hexagonal lattice is not a typical Bradley lattice, and the dispersion relation looks like this. So we have two kinds of permeance, and we can classify that. So here is another interesting behavior by pictorial. What are the basic differences between metals, insulators, and Dirac material? So again, we have plotted this the energy in the y-axis and the crystal momentum in the x-axis. So this insulator is there, this metal is there, and Dirac material, look at this Fermi energy piercing to this only a single point. So this is the characteristic features of the metal and Dirac material. Here there are lots of excitation can be done, but there is a few excitation can be done, and here there are very less excitation. This on the whole actually affect the density of states. So in this graph we are trying to show the basic difference between the density of states between metal, semiconductor, and graphene, which is a Dirac material. So y-axis has been plotted the density of state, and x-axis is the energy. So density of states is defined as the number of states lying between E and E plus E for a unit volume. And so look out at this metal after this Fermi energy, all the states were filled up, and this mode aspire to be. So this is empty. Semiconductor, we have a gap between valence and conduction band, so there is filled band and empty band. And graphene, look at this, at the EF, this density of states is exactly true. So it is this zero density of states at the metal, it tells you that this is not the metal but semi-metal. Okay. Or you can say it's a semiconductor, a zero band gap. Both these two nomenclatures are well suited for this graphene or titanium. So let's look at this electronic structure. So what are the spatial hydrogen bonding? That is sp2 bonding. So the states are electrons are given this one S2s and 2p2. So there are sigma and pi bonds. We know that these sigma bonds are exceptionally gives you the rigidity. So they are not so much mobile like the pi electrons. So essentially the band structure which is controlled by this particular electron is called the pi electron, which allow this conduction. So there are some kind of, again, difference between the graphene and traditional 2D material. I will not go to the details of this thing, but only one thing I would like to tell you and share with you. There is some called Klein tunneling. This is a very important tunneling which is seen for relativistic particles, and this is seen for the also Dirac material. And the question I would like to tell you here is that in a normal tunneling, what happens that you have this width and height is blurred, then this tunneling will be very small. In the non-relativistic one, this is reversed in the case of relativistic situation. That's called the Klein tunneling. And there are kind of many other properties. For example, graphene can be made as much thinner as possible, very few nanometers, and so that this traditional 2D electron gas can be actually seen in a kind of typical quantum well or radar structure, which is often actually studied in case of quantum Hall effect. And because of this particular preparations of this 2D electron gas, there are many traditional applications in graphene like quantum Hall effect, anomalous Hall effect. Another interesting feature is that graphene is found to have some finite minimum conductivity even in the vanishing of dark area. And this is an important issue which has been already appearing in the field effect transistor. So let's start with this geometry and at least show and share with you that how does this linear dispersion come in this particular graph. So let me, in a few slides, I will share the tight binding calculations to share with you that this dispersion is really linear in momentum in the low energy limit, that is K tends to be limit. To do this thing, first we'll have to calculate the Bravais lattice structure, because this is not the Bravais lattice. It has been the unit cells for this particular graphene, and this has been calculated here, and this is tau 1 and tau 2. So we can calculate this the lattice transitional vector like this in one A times, in one into A times. And the reciprocal lattice vectors get to satisfy Vi dot J in Aj equal to twice by A time. So lattice vectors A1 and A2, as you can say, check that they are not orthogonal. So given this thing, we can now calculate this reciprocal basis vector Pi, which is shown like this thing. And these are the below-zone spatial symmetric points, that is gamma, most symmetric point K equal to 0, and N and K. So I just remind you to, in this sense, K will turn out to be the Dirac point. So we'll find out that this is the point where this dispersion in the sum is 0. So these are the 2 points which are equivalent K and K dash. So these are the points which I try to show you in the next few slides. So you can calculate this matrix element of the diagonal element and the off diagonal element, and calculate this hopping parameter, this particular TK, and then you find out this particular simple 2x2 matrix to find out the eigenvalues of the system. And once you plot these eigenvalues in the AX, KY plane, you look out this particular structure, and this is the points where this dispersion is managed. Okay, so K and K dash, which are just shown in the previous slide. So now, if you do a little bit Taylor series expansion around these Dirac points, and then you will find out this matrix element and the space vectors will turn out like this, where this H cross here, the VA with the forward velocity is related to this lattice constant and the hopping parameter like this. And once you go to this particular algebra, you will find out the beautiful matrix transformation which I showed in the first slide. So this is the writing down of this graphene Hamiltonian in terms of this Pauli spin matrix. Remember, although this condensed matter system is basically a low energy phenomena, it has nothing to do high energy phenomena, but we have been able to capture the zero mass limit of the Dirac equation in the appropriate limit. So nothing to do in the high energy limit. The velocity which the Dirac fermions do move in this particular lattice, that is not the speed of light. Nothing Lorentz invariance, nothing is required there. So we don't have to think in that particular line. It is just an analogy to think about that this is a linear in P. And the Fermi velocity is not the speed of light, but c by roughly 300. So this is much less than the speed of light. So with this thing, what we have learned so far is that there are two kinds of points which are non-equivalent. The graphene structure is having this Dirac relation, and if you further plot the density of states, it looks like a V-shaped graph. This is the Fermi energy, so the energy level has been subtracted, and this is a particular inversion of this thing, and K and P dash these are actually symmetric Dirac points. So one of the most symmetric point is the gamma. So you can calculate all the other points which are related by the equivalent points. So this is the same thing which I am again repeating, that telling you that the semiconductor and graphene, they are actually separating by only the quadratic and linear dispersion. And if you take these relativistic relations in the non-relativistic limit, you get this particular. But if you have a massless thing just like the photon, you get a simple Dirac-like spectrum like linear impedance. And there is an important feature also in 3D that these electrons, you can also write down this thing, whereas as I told in the early, that is 4 cross 4 massless Dirac Hamiltonian, you can transfer that both things. So this is fourfold difference in case of 3D electron. So again, refreshing my knowledge, so far we have understood and learned that this ordinary 2D materials they obey to the Schrodinger equation, whereas the 2D Dirac materials they obey, of course, the Dirac equation, the low energy limit at some special point, not all points. Remember that thing, because we have shown in K and K dash, not in gamma, not in M. And the energy momentum relation is quadratic. This is a Dirac-like, that is supposed to be linear. There is two other things which I have not covered, but I am sharing with you for its kind of typical Landau levels problem. If you apply magnetic field to the material, it will turn out that these energy levels are discrete, and this energy level is proportional to n, whereas in this case the energy level is square root of mod n, and the main important thing is there this 0 point energy level is around half h cross omega c. Omega c is the cyclotron frequency, and here it can be put close to the zero energy. That's important. Okay, and this is important for the particular piece of for the fabrication of device. Now, as I have pointed out that effective masses has some problem, so let me address that thing. We know that effective mass is related by this particular relation, that is the m star inverse is related by 1 upon h cross square L to E del K squared. But we know that this is not the appropriate quantity because it is scalar, but it is inherently a tensor, so we should try to calculate by this thing, and that's why this relation is applied here. And if you put this calculation, do some little bit algebra, you will find out the effectiveness inverse that satisfies a very nice 2 cross 2 material which has this particular matrix called M theta. Now M theta is a very nice property. If you look out that thing, that the trace of this matrix is 1, where a determinant is 2. That tells you that this eigenvalue is 1 is 0, another is 1. So if you do this analysis, you can find out in one direction the effective mass is heavy, that is infinite, and another is finite. So there is the anisotropic, longitudinal, and transverse direction of effective mass in this particular point. And also the density of states electronics properties can be also modified. For the Dirac material, the specific is goes to T per D, whereas for the metal, for any dimensions, because of the Pauli exclusion principle and this particular quadratic phenomena, that is the momentum related quadratically, it will be always proportional to P. Here is the proof of this theoretical predictions of angle resolved photoemission spectrum data, which is y-axis is binding energy and the x-axis is the wave vector. So if you look out, these are the points of the presence of these Dirac points, and you can actually calculate and observe this thing by varying the scanning over this different K values, and this matrix exactly the. So your next question is that is this the only material which can have that Dirac property? The answer is no. There are many more materials that come up in the last few years. So that the view of 2D materials, which is shown by the slides, which also share this thing. Then the question is that how many of them also share this Dirac force? So the elemental of all these materials which have been found out in recent times, which are all 2D materials, which also share this particular Dirac point. Now the question is that why are Dirac materials rare? Because this is satisfied, as has been rightly pointed out by Wang and al. In recent times, that there must be some stringent conditions on the Hoping integral which shall be satisfied by this particular material. So T1, T2, T3, T4, these are the nearest neighbor, next nearest neighbor, next nearest neighbor, and next nearest neighbor Hoping parameter. So this must satisfy these conditions. And not only that, there must be having some other important criteria which is related to the hexagonal symmetry and other particular parameter symmetry, that for a typical kx, ky real value, they has to have a solution in the phase space. Not every EK must have a solution, but for a real band structure, you must have the values for real values of x and ky. So these are the kind of typical, and also I have pointed out that the Fermi level should lie at also the Dirac point. So now we will try to adopt two techniques. At least one has been already shown you, that the tight bending model and the density function theory. And density function theory is the novel material property investigating tool, where you can predict new materials and you can also calculate the band gap and other physical properties before it is synthesized. So this is a basic introduction to this concept of density functional theory, where this density, which is a real quantity, which actually play an important role into the in contrast to the conventional Schrodinger wave function picture. And for this particular reason, Nobel Prize was awarded to Kohn in 1998 in chemistry. So here is a self-consistent case. So you start with a particular density, and then you try to solve Kohn's and one electron equations, and there is the exchange potential, external potential, and the other central potential, which you can addict here, and then you try to solve this problem consistently. The crux of this method is that what kind of particular exchange correlation can be included. There are many kind of exchange correlation. Here you will have to pay certain attention to solve this particular problem. So here I am showing on few graphs that how this band structure of graphene nanotable can be calculated on a typical laptop program. This is a graph of the typical Nobel laureate lecture notes. So this band structure of graph, you can see that if I add many ribbons, the band structure, this is the y-axis is electron energy, K is in the x-axis. Sometimes it is touching, and sometimes there is a gap. So depending upon the number of kind of rings you attach to it, there is a change of the properties of the material. Namely, it could be metal, it could be semiconductor, insulator, depending upon the band gap. So here is a very simple way of running out your simple structure. Now there are many more kind of softwares which are available. You can down this program. Okay. So now next few slides we are trying to concentrate on the typical work which I am doing for last couple of years. This is one of the work in the graphene network where we substitute boron and nitrogen, and these are different points. So T1, B1, U1, F1, these are basically the typical inequivalent point, whereas A, C, D, E, these are basically the equivalent points. So one denotes the non-equivalent point, and without one, that is the equivalent point. You have the very simple basic question: do you see any change in a band gap in the by grouping these particular atoms? But at this stage, we would like to share one important aspect: that why we would like to open a band gap in this particular graphene. Remember, in case of any device applications, you need to have a proper control of electrons. Here, because this Dirac point is a single point, the electrons without any scattering, it's ballistically transport very fast, and the conductivity is quite large. But if you do not control that conductivity, you cannot use as a kind of typical device. That's why transistor is often very much successful, because in the your doping is done in the base, so that you can control the current from the transistor 1 and emitter to collector, right? So here we have to open a band gap so that you can control the flow of current. So opening of band gap can be done many ways. It can be either applying add atoms, replace some of these carbon by other kind of atoms in the same group, like boron and nitrogen, because the atomic radius are very close to that thing. And also you can attach some other kind of organic group of molecules, or you can apply some electric field or some kind of strain. There are many techniques of opening this band gap. So this is a work from our group, which published in 2014. We have shown that if you dope this boron and nitrogen, also co-doping. Co-doping means you do not change the particular electron number, because nitrogen has extra electrons and boron has less one electron, so you do not change the number of electrons in the system. In co-doping, you find out this is the change in band gap of the system as you change the doping concentration. And it is really surprising and also very easy to see that this was predicted few years after the predictions of this 2014 to 2018. The group in Taiwan, they actually found out this tangent variation, exactly what was predicted by. So now we are moving to tetragonal graphene. So the questions we would like to answer or check it, that is honeycomb is the only prerequisite. Can it be observed in non-honeycomb like that thing? The answer is yes. Here is the structure of tetragonal graphene, which is the space group is giving P4 mm, and the lattice constant, bond length, etc. are giving. And if you do this time bending calculation and DFT calculations, you can see that there are points where we can have this structure or not. Okay, so the density of states at the Fermi energy that should also go to 0, and you can see that there is this analytical structure can be matched with the type DFT calculation. And here is another work on the tetragonal graphene sheet, which will change this the flux associated with these two square ring and the octagonal ring can also change the band gap of the system. Okay, this is analytical result. So this is a typical flux model where you have to change this hopping part by like doing that thing. This is interesting. Another way that using this RSRT, that is real space denomination and group calculation, you can decimate to a very one or two lines kind of one-dimensional system. That's why you can do this analytical calculation, and you can check that this the gap like here. You can see that definition of flux. Okay, there are possible applications in the tetragonal graphene. You can use as a kind of carbon monoxide gas sensor and current rectifier. I'm not going to the details of these things, so that you can check it in the kind of some papers. We are now moving to the graphines. So this is another allotrope of graphene where instead of double band we use acetylene linkage, the triple bond. And there are many possibilities, and this has been experimentally found out in years back, 2016. And we have also worked on this particular materials, and there are many varieties of this particular structure, which I have shown it here. And you can classify doing by analytical calculation. Again, the tight banding model coupled with the DFT calculations with this RSRG scheme, we can find out the band structure with these particular equations for graphite and other particular systems. I'm not going to the details of that thing. And finally, we are almost coming to the end towards our journey of this material. Recently, we have worked on a double Dirac codes in the air graphene system. This is again a tight bending approach along with the typical DFT lasers. So we have shown that both from the RSRG scheme, there is Dirac point not as the other most symmetric point, little bit away from the symmetric point, as you can see that thing. This is the DFT results. Okay, these are the most symmetric points, but we have found out little bit away from that thing, and the dispersion relation which have been calculated analytically by this RSRG scheme is shown it here. So now the question is, can we control the two Dirac codes? That means one Dirac cone we can open a gap and the other thing can be add like that. The answer is yes. There are some conditions of the hopping parameters where you can, in one case there is Dirac cone there and there is the band gap here. In another case there is the band gap here, but there is this Dirac cone here. So we can control via this hopping parameter. This is one way of opening band gap, keeping the other Dirac cone like the same as the Dirac cone where dispersion is allowed. Okay, so let me tell you about the significance of these Dirac materials, where we have shown that there are kind of Dirac materials, the experimental light, which I would like to share with you. There is, it is transparent to light, visible light, and there is a very interesting question that the absorption coefficient at the K equal to 0 point, that is the long wavelength, gives you a very interesting result that is called 5 times the fine structure constant squared by H cross C. So this is one way, a verification of our fine structure constant. You remember that in fine structure constants are often appearing in the field branches of physics, in atomic physics, relativistic, spectroscopic correction, as well as in the high energy physics, particle physics. All these scattering of systems are actually written in terms of fine structure constant. But there are two incidents from condensed matter physics. One is from this Dirac material, another is from the quantum Hall effect, where you can actually calculate this value of fine structure constant in one part in 10 to the power 8 or 10 to the power 12 order. So this is after the decimal point. There are many more numbers you can take it. Often we encounter for solving problems 1 by 137, which is not exactly 1 by 137, but 1 by 137 points of decimal number. Here is one of the occasions that to this transparent and this absorption coefficient at the long wavelength image, we can calculate this fine structure constant. This can be also opaque to same light when it falls in from different directions. Because of this, again, it's a good point. There are many applications to transparent conducting films. That is common example is the touch screen, which is used in mobile. It can be used. There is opacity, and the semi-direct materials can also be used as a clean energy technology, having some important thermoelectric properties for low power applications. This is to be thought as an alternative to energy technology. And another point, which is the more attraction nowadays, that robustness and the topological aspect of this material. These materials can be transformed to various new other materials like wine kind of topological material, wild metals, and other kind of different spin involved, spin conductivity involved, Dirac material, topological insulator, all these kind of properties which are come in a big way in last few years can also pave the way of understanding. So these things, there are some few references, and I'm almost through this lecture of this Dirac material, and I wait for your comments and suggestions, and I'll be happy to give you some answers which I'll be giving in a few minutes later. Okay, and there are more than only Dirac materials. There are other kind of objects which we are trying to look out in the next few years with the tight banding model as well as Dirac DFT materials. Now remember, if you have more than few layers, then of course there is this typical Dirac material property to be there. So bi-layer and tri-layer, there is the usual kind of not Dirac material. So that has been seen in experiment. So many more materials that are coming in few years. Not only the graphene allotrope, I concentrated here on the graphene.
Sir, are you there? Sir, we can't hear you. Hello, sir. Sir, are you there? I think some technical problem has occurred.
And here are my group of students who are working with me for the last few years. So I will conclude here. Thank you for your attention. Thank you again.
Thank you, Professor Jana, for your nice demonstration. So, with your permission, now we will go for question and answer session. So, can I go for it, sir?
Sure.
Okay. So, there are several questions. So, first question is, can graphene be used in medical science?
People are thinking, but I am not sure because most of the cases people are using nanoparticles, not the graphene. But as I have told you that the field effect transistors, that has come to the market. Okay, so if that can be used in medical science purpose, I think it is okay. But mostly for diagnostic and other things, nanoparticles are used, not the graphene.
Okay. Sir, second question is graphene eco-friendly?
Yes, it is eco-friendly. There is no problem of toxicity till date. Although there are some kind of cadmium oxide and cadmium sulfide which are nanoparticles, but graphene till date, there is no report of toxicity. It is eco-friendly. Fine.
Okay. Okay, sir. Next question is, edge states doesn't occur in case of armchair configuration. So still,
yes.
Can it be used for application purposes?
Yes, it can be used because edge state has a particular topology. It has some zero modes and other things. Conductivity can be controlled. But the other things can be also controlled in armchair and other things. There is no problem. Edge states also gives you kind of some non-magnetic structure. Remember, graphene is basically a diamagnetic. It does not show any magnetic property. So on the other hand, edge states that actually shows its magnetic property. So in that case, that sensor and other things can be used.
Okay. Sir, next question is, why the 0 point energy of graphene is 0?
Zero, because this exactly meeting at the Fermi energy. We are measuring the Fermi energy. From the Fermi energy, we are measuring the energy level. So that's why it is 0. But in the case of your conventional material, because of the 0 point energy oscillation, the electrons are harmonically bound. Here they are not harmonically bound. So because of harmonically bound, they have non-zero point energy. So that's why this is half H plus omega. But here it is not. Again, it is related to the linear and quadratic dispersion.
Okay. So last question is, sir, any future promising application of Dirac materials?
People are mainly bothered about, as as I have told you, the electronic band structure and the band gap opening, controlling the electrons. Once this controlling is perfect and repeatable, I think people can use for thermoelectric purpose. Figure of merit and good thermoelectric material can be used in graphene. But as I have told you, still that there is not kind of promising application so far.
Okay, sir, there are no more questions. So, on behalf of organizing committee, we sincerely thank you for this nice session, for being with us, and the beginners will be surely benefited from this talk. So, thank you, sir, again.
Okay, thank you again for inviting me for this webinar.
Okay.
Thank you again.
Okay, sir. So, we will go to the next technical session. Our next speaker is Dr. Paramita Dotto. She is now working as a postdoctoral research fellow at Department of Physics and Astronomy, Uppsala University, Sweden. So, in brief biography, she received her BSc degree and MSc degree in physics from Jadavpur University. She did her doctoral research at Theoretical Condensed Matter Physics Division, Shakha Institute of Nuclear Physics, Kolkata, and she received her PhD degree from University of Calcutta in 2015. After that, she joined Institute of Physics, Bhubaneswar, as a national postdoctoral fellow funded by Science Engineering Research Board in 2016, and then she moved to the Uppsala University, Sweden in 2018. She works on quantum condensed matter physics. Her research interests include quantum transport and topological aspects of low-dimensional systems and superconductivity also. So today, she will talk about thermoelectricity in superconducting junctions. So I'd request Dr. Paramita Dotto to deliver her presentation. Ma'am, it's over to you.
Thanks. Hi, can you hear me?
Yes, ma'am.
Okay, thanks. Thanks, Professor Nandi, for this nice introduction. And good afternoon, all of you. Welcome to my talk. So let me start sharing my screen. Can you see my?
No, ma'am. Still now it's not.
Can you see my screen?
No, ma'am.
We can wait. It's not.
No, still not.
Since I'm already presenting, so I don't have this option.
So,
Is there anyone else presenting?
no, ma'am. No.
Because my option, my second.
Okay. Do one thing, madam. Please, can you please sign out and rejoin again? I think that will solve the problem. Hello. Ma'am, please wait. Probably some technical problems occurred. I'm looking into this. Sir, you please stop presenting your screen. Professor Chakraborty, can you hear me?
I am not sharing, Atanu.
Okay, sir. Okay, I'm listening.
Paramita, your microphone is muted.
Hello.
Yes, I can hear you, madam. But
Hello.
please. Yes, we can hear you. Hello, ma'am, we can hear you.
But Paramita's microphone still shows it's mute.
Madam, your the microphone is showing muted. So please unmute your microphone.
Atanu, the video seems paused.
Ma'am can rejoin.
Madam, you can rejoin. You can sign out and you can rejoin. I think that will solve the problem.
অসুবিধা হচ্ছে।
Shagotati, whether she has joined or not.
No. Ask her to join again.
Okay. So participants, please have patience. Some technical problems occurred.
Issue, it will be solved immediately. No problem. Ask her to try once again.
Hello.
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 Hello, ma'am.
Can you hear me? Can you hear me?
Yes, miss.
Yes.
Sure.
Okay. So I'm very sorry for this problem. Actually, so suddenly my internet
Always
connection
after-
got.
No problem. No issues. You can carry on.
Okay. Yeah. Yes. Yo, so I can share my screen. Please have a look and confirm whether I have. So can you see my screen?
No, ma'am.
No, not now, ma'am. Yes, it is coming. Yes, it is coming.
Ma'am. No problem. Okay, fine.
Yes,
It has come. Thank you. Okay.
yes.
Is it fine now?
Yes.
Okay, yeah. So good afternoon, everyone. Welcome to my talk. Myself, Paramita Dotto from Uppsala University, Sweden. And I would like to thank the organizer and also especially Professor Nondi for this invitation. And I wish good health in this pandemic situation to all of you. As asked by Professor Nondi, I will be discussing two of my recent research works. And I will not be presenting, of course, all of the results I have in those two works. And I will try to simplify the whole story as much as possible. Okay, so today I'm going to talk about thermoelectricity in superconducting junctions. So why we are considering superconducting junctions and what do I mean by superconducting junctions? Before discussing those things, let me start with a brief introduction to thermoelectricity. Can you see the change in the screen?
Yes.
Okay, thank you. So thermoelectric effect is an interconversion of thermoelectric voltage and temperature gradient. Suppose you have a conductor and you maintain two different temperatures at the two ends of the conductor. So after some time, we will see that the current will be flowing through the conductor. So that means here the temperature difference is converted into an electric voltage. Because this is the so-called, the well-known phenomenon is called Seebeck effect. It's named after the German physicist Seebeck. And the vice versa is also true. So that means if you have a current carrying conductor, and after some time, we will feel the temperature difference or heat is generated inside the conductor. So here the electric voltage is actually converted into the temperature difference. So there is some well-known or basic, or you can also say some fundamental thermoelectric effects, as I mentioned already, the Seebeck effect, and the vice versa is called Peltier effect, and there are some other effects like Thomson effect. I will come back to the details of this effect after some slides, but let me tell you something else in this slide. So this kind of thermoelectric effects is also true or also happens in presence of spin. If we consider the spins of the electrons, it's very similar to what we find in case of spintronics. In spintronics, we can see the interconversion between the spin current and the charge current. And here we can also have interconversion between the spin current and the heat current. And the field is, the associated field is called spin caloritronics. But today I will concentrate only on the thermoelectric effects, which is the interconversion between the charge current and heat current. So now you can ask one question that why should we study thermoelectricity, or why do we study thermoelectricity? We often see some unwanted heat is generated in many devices. So if we can extract that excess amount of heat and cool down the system and use it elsewhere, so then we will have some dual advantage. We will be able to cool down the system, and also at the same time, if we can use that excess heat somewhere else, that will also be useful. One of the simplest example is that we often see the unwanted heat is generated in CPU. If you can extract, if you have some device that can extract that excess heat and convert into electricity, so then we will be able to cool down the CPU. That will enhance the efficiency of that device, and at the same time that extracted heat can be converted into electricity, and that will be helpful in power generation too. So we'll have this dual advantage, and the devices which can actually do this task, we call it energy harvesting device that can convert the waste heat into electricity. So there are some requirements to have to enhance the efficiency of that energy harvesting device. Like we can use very good thermoelectric material. At the same time, we can make this conversion process as efficient as possible. So today I will not talk about the conversion process or anything else. I will only concentrate on the good thermoelectricity. So the question I'm asking, how to identify a material or system. You have been given a system or material, so how to identify that is a very good thermoelectric. From theoretical point of view, we can calculate values of those good electric identify equation is discussed which relate
Ma'am, we can't hear you. Hello? Hello, ma'am, we cannot hear you. Oh, again, some technical problem occurs probably. Shagotadi, whether she has left or
No, I can't see her. I think she has left. There's a issue, technical. I think there's some connecting problem. She'll be back. I think she's not.
yes, actually there is some technical problem. Okay, just participants, please hold for 2 minutes.
Yeah, there's no problem. She'll be coming back. It was going on fine.
Shagotadi, whether she has joined or not.
No.
Okay, actually, her area is actually very near to airport. That's why some internet problem occurs several times.
অতনু,
Yes,
ওনার বোধহয় কিছু সমস্যা হয়েছে, ওনার সঙ্গে সরাসরি যোগাযোগ করো।
yes, I'm looking into this matter, sir. Sir, please hold. Due to some internet problem, probably she has left. We will try to look into this matter. We will get back as early as possible. So please have patience.
She has joined. Hello, she has joined. She has. No, again she has gone out.
So we are trying to connect her. So please have patience, participants.
দেখুন এখন নেটে হতে ইউটিউব দেখুন আপনাকে আমি কাস্টম এটা দিয়েছি এটা চলছে প্রথম থেকে কিন্তু এবার এতক্ষণে নিয়েছে আর কি স্ক্রিনটা আমি আপনাকে আমি তা আপনাদের কলেজের ইয়েতে আর আপনাকেও কাস্টমটা দিয়ে যদি কেউ ঢুকতে চায় এখন খুব সহজে ঢোকা যায় বলছে পুরোটাই প্রথম থেকে কিন্তু কিছুতেই লোক বুঝতে পারছে না স্ক্রিনের জন্য আর তাই যদি কাস্টমটা বার করে কী করে কাস্টমটা বার করতে হবে তাই আমি বুঝতে পেরেছি সেটা বার করে এখন রেকর্ডিং পুরো আছে সব আছে ওটা একদম ড্রাইভে চলে যাচ্ছে ডাইরেক্ট আমি একদম অরিজিনালি রেকর্ড Have you called her, Atunu?
Has she joined, Shagatadi?
No, no, I can't see her. She had joined for a second and again she left.
Shagatadi?
No, I can't see her.
Oh,
She is not here.
okay. I am trying to connect, but her cannot connect. I will try. Okay.
Okay, no issues there. We have a lot of time. We can wait. No, sorry, participants. Please bear with us. Participants who wants to can join through YouTube also, because for technical reasons it was not working in the beginning, but the program is live, so I have also given the YouTube link in the chat box, so you can access that and you can choose to go on YouTube too if you want, because because there's no issues. You're free to enter and leave the meeting then. So for that reason, I have given it. There's some technical issues, so it was not working in the beginning. Hello. Nice, tasty. দাঁড়ান। আপনি ফ্যাকাল্টিতে দেখুন, ফ্যাকাল্টিতে দেখুন।
So some technical problem occurs. We are trying to connect her. So please have patience, participants. So we are trying our level best.
connect her? participants, you may wait. She'll be coming. Don't worry. We are trying to connect her. বেশ হচ্ছিল জানো, এত সুন্দর present করছিল। আর নেই লাস্ট। হ্যাঁ 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 ইউটিউব লিঙ্ক দিয়ে দিয়েছি সব। পুরোটাই তো হয়েছে, লিঙ্কটা দিতে পারছি না। দেখো পুরোটাই আছে, শুধু একটু অন্যভাবে আছে। আমি দেখো আগে যে লিঙ্কটা দিয়েছিলাম তোমার এইচটিপি স্টুডিওটা হবে না, বুঝেছো? এটা হচ্ছে এইটুকু YZSK ওটা একই আছে। হ্যাঁ, তার আগে HTTPS youtube.b অন্যরকম। দেখো তুমি আসলে দেখো তুমি দেখো, আমি এটা মিলে দিয়েছি, এটা হচ্ছে লিঙ্ক। হ্যাঁ দেখো, আর তোমাকে যেটা দিয়েছি দেখো, আসল লিঙ্কটা আলাদা। হ্যাঁ ওই লিঙ্কটা হ্যাঁ এক্ষুনি পাঠিয়ে দিচ্ছি, ওটা তো সবাইকে পাঠাচ্ছি। এটার একটা স্টুডিও লিঙ্ক চাচ্ছিল, যেটা সবাইকে দিতে পারছি। হ্যাঁ বলো কি হলো? সে আবার সৌরভদের এত তাড়া কিসের? সে আবার কি সুন্দর প্রেজেন্ট করছিল। ইন্টারন্যাশনাল কল করা যায় না? দেখো ইন্টারন্যাশনাল কল করা যায়? ও আচ্ছা, ও তো বললো, ও তো সুন্দর প্রেজেন্ট করছিল, ও তো সুন্দর প্রেজেন্ট করছিল গো, হঠাৎ করে কি হলো? মেসেঞ্জারে মেসেঞ্জারে কল করছো, হচ্ছে না, হচ্ছে না। হোয়াটসঅ্যাপ করলে হোয়াটসঅ্যাপ ওরা ওরম করে না। তুমি বলো, তুমি ওর হোয়াটসঅ্যাপ নাম, তুমি আমাকে নাম্বার, হোয়াটসঅ্যাপ নাম্বারটা দাও তো, আমি দেখছি। হোয়াটসঅ্যাপ কল করবো, হোয়াটসঅ্যাপ কল করি, হোয়াটসঅ্যাপ নাম্বারও দেয়নি। আরে কোনো ব্যাপার না, এত প্রজেক্ট করেছি না, অনেক জায়গায় আমাদের present করতে পারি, কোনো ব্যাপার না, ঠিক আছে নাম্বার
Oh my God!
ওরা বলছে শেষ করো। আরে আমার সাথে ট্রায়াল দিল পরশুদিন ভদ্রমহিলা, মহিলা আমাদের মতো বয়স। হ্যাঁ পারমিতা, এই সুইডেন গেছে কবে। ওর কোনো ইন্টারন্যাশনাল নাম্বার নেই ওর। হোয়াটসঅ্যাপ নাম্বার। বেশি এ করা ভালো, বেশি করেছে তো ওরকম এই করতে হবে। সে করো। আমার মতো ওরকম খুলে দিতে হবে না কিন্তু একশো দশজন রেটিং। ওরা তো আমেরিকা থেকে প্রবলেম হচ্ছিল কিন্তু ছুটে পড়েছে। চলছে না এই লিঙ্কে চলছে না এই লিঙ্কে চলছে। ফোনও নেই, ফোন নেই, ফোন কানেকশন, মেসেঞ্জার, নেট না থাকলে তো মেসেঞ্জারও কাজ করবে। ওরে আয় রে। হ্যাঁ হ্যাঁ কী হলো কী বলছি? হ্যালো হ্যালো বলো কী বলছে? হ্যালো
Hello. 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 Can you hear me?
Paramita di, are you listening me?
Yes, yes.
Hello, Paramita di.
yes she's joined.
Yes, I'm listening. Yeah, it's fine. Am I audible?
Yeah.
Hello?
Yes you are audible.
Hello, we cannot listen you.
You are audible.
Okay. So was it fine throughout the talk?
So sound problem is there. So please increase your sound. We cannot hear you.
Can you hear me now?
No. Still faint.
Yes we can hear you. We can hear you.
Maybe I can try one more.
Yes,
I can.
you can share screen. We are hearing you. You share your screen, ma'am. We'll see to.
how much did you?
You're audible. You're clearly audible now. You share your screen now.
But how much, on which slide I was there for when I was?
So second slide.
Oh, only second slide.
Yes, yes.
Okay. But it was showing like I had the connections throughout. Hello.
Yes, you're audible.
On which slide I was?
Next.
Ma'am, present your screen.
No, previous one.
This one?
Yes, this one. Up to this one, we have heard you.
Oh, okay. Okay. Sorry for the connection I was on. Please, then I will ask you time to time, so that to make sure that I have the connections. Is it fine now? Hello.
It's fine.
Yes, fine. But can you increase slightly your volume?
Yes. Can you hear me now?
Yes,
Is it better now?
yes, it's fine.
Better, but still.
Hello.
Yes, ma'am, you carry on. No problem.
Okay. So what I'm telling you that what is thermoelectric effect? So thermoelectric effect is the interconversion of electric voltage and temperature difference. Suppose you have a conductor and the current is flowing through the conductor. So after some time, we will see that there is a temperature difference between the two ends of the conductor, which is the so-called Peltier effect. But if you have a conductor and you maintain the temperature difference between the two ends of the conductor, so after some time, we will see that the current will be flowing through the conductor. So there will be a conversion between the temperature gradient and the electric voltage. So this is a well-known effect called Seebeck effect. And there are some other fundamental effects like Thomson effect. So I will not be talking, or I will come back to this effect after some slides. But all these thermoelectric effects are also true in presence of the spin cars. If you consider the spins of the electrons, what is very similar to what we find in case of the spintronics. There is an interconversion between the spin current and the charge current. And but here the field is called spin caloritronics. We can have the interconversion between the spin current and the heat current. But I will not concentrate on the spin of the electrons today. Only we will have the conversion between the charge current and the heat currents, the so-called thermoelectric effects. Is it fine? Am I audible?
Yes, ma'am, you're audible.
Hello?
Yes, ma'am.
Okay. So now the question is, why do you study thermoelectric effect, or why should you study thermoelectricity? So we often see some unwanted heat is generated in many devices. If we can extract that excess amount of heat and convert into an electricity, so that will be very useful. We will have the dual advantage. In one case, we will be able to cool down the original system. At the same time, we will be able to generate some electricity out of this waste heat. So what are the requirements for these? Are the systems called energy harvesting devices. And there are some requirements to make this energy harvesting devices more efficient. We can have some good thermoelectric material. At the same time, we can make this conversion process as efficient as possible. So I will not talk about the conversion process today, but I will only concentrate on the thermoelectricity, or how to define a given system or material, whether it's the good thermoelectric or not. So I can just mention quickly here one very simplest example. We often see some unwanted heat generated in CPU. If we can extract the excess amount of heat and cool down the system, and you can use it elsewhere, then we will be able to generate some electricity out of this waste heat, and at the same time, we will be able to cool down the CPU. So that will enhance the performance or the efficiency of our device. So the question is how to identify how to understand whether is a given system or material is a good thermoelectric or not. So can you see the change in the slide?
Yes.
Hello?
Yes, ma'am. Yes, ma'am. Yes.
Okay, thank you. So how to identify a given system or material is good thermoelectric or not? We can calculate some theoretical point of view. Actually, we can calculate some thermoelectric coefficients, and looking at the values of the thermoelectric coefficients, we can say whether it's a good thermoelectric or not. And to define those thermoelectric coefficients, let me start from the basic equation, which is called the Onsager matrix equation. And we can relate the charge and the heat current to the applied bias or the temperature difference from there. It's actually we're connecting the flux to the driving force here. And there's all the coefficients can be expressed in terms in our matrix form, which we call the Onsager matrix. The diagonal elements actually describes the conjugate processes, and octagonal elements describes the non-conjugate processes. Here you will have some like I can tell you in more detail. For example, if we do not have any temperature gradient, so the delta T is 0, we have a conductor and we apply some bias voltage there. And we'll see that the current will be flowing through the conductor, and following the Ohm's law, we can find this charge conductance from there. So this L11 will give us the charge conductance. And on the contrary, if we have only temperature gradient, no bias voltage, then we will be able to find the thermal conductance at the same time. And there is some these off-diagonal terms will give you the non-conjugate processes. Like if we apply the temperature gradient, how much voltage is induced in the system, that we can find from these off-diagonal terms. And I have written both L12 and L12 in both of these places because they are equal to each other following the Onsager reciprocity theorem. And the main process is that, so the summary is that we can calculate some coefficients which like thermal conductance, which measures the ability of the heat transfer driven by the temperature gradient. We can also calculate the Seebeck coefficient, which is nothing but the induced voltage per unit temperature gradient. And the Seebeck coefficient can be extracted or expressed in terms of the base temperature of the system, and the alpha, which is called the thermal coefficient, and the charge conductance. Similarly, this alpha is actually L12 and G is the charge conductance, which is L11. And from the engineering point of view, we often calculate the thermoelectric figure of merit, which characterizes the power conversion ability of the thermoelectric device. And this thermoelectric figure of merit can be expressed in terms of the Seebeck coefficient, charge conductance, base temperature, and the thermal conductance. This K is actually kappa plus some correction factors there. Now, it is hard to find to any material or system where we can find the thermoelectric figure of merit higher than 1. For any device, if it's higher than 1, then we can say it's a very good thermoelectric material. Now, looking at the values of the Seebeck coefficient and the figure of merit and the thermal conductance, we can say that whether the given system is a good thermoelectric or not. Am I audible, Jill? Hello?
Yes, ma'am.
Okay, thank you.
Yes.
Okay. So the question is...
Yes.
Okay, the question is, what is the present goal? So what I am doing here, to show that, I want to show you that a superconducting junction can work as a very good thermoelectric system. And the junction I am considering is ferromagnetic superconductor junction. Now, naturally, the question arises, what do you mean by superconducting junctions? Are junctions made up of superconductor and non-superconducting materials? Suppose you have a non-superconductor. I am talking about a very conventional superconductor. And we attach a non-superconducting material to that, then we will be able to form a junction or the hybrid structure. And I am referring to this junction as a superconducting junction. And on top of that, we are also considering some interfacial layer. Is a very thin layer in between the ferromagnet and the superconductor, and which is responsible for some spin orbit interaction. Also, it will include some barrier, but I will come back to this point later. Just for this slide, I can mention that okay, we have a non-superconducting material and a superconductor, so they are attached to each other to form a hybrid structure, and this system I'm referring to as a superconducting junction. So why superconducting junction? Why not bare superconductor? A bare superconductor is not a very good thermoelectric. In literature, already there are many studies, both theoretical and experimental, which have already proved that a superconductor is not a good thermoelectric at all. So if we can combine a non-superconducting material and attach the non-superconducting material to the superconductor to form that hybrid junction can act as a very good thermoelectric material that I will show you in this presentation. So can you see the change in the slide? Am I audible? Hello?
Yes, ma'am, you are audible. Yes, you are audible.
Okay, thank you. Sorry for asking so many times because it's the connection I have to. Okay. So there are some motivations like this. So in literature, there are some works which have already proved that a superconducting junction can act as a very good thermoelectric. In 2012, Kalenkov et al., they have shown that if we have a conventional superconductor and dope some magnetic impurities in there, then we can find some strong enhancement of the thermoelectricity. Next year, in 2013, Macon et al., Macon, Estruik and Belzig from University of Constance, they have shown that, okay, we can also have some non-local thermoelectric effects in this if we have attached a ferromagnet to the superconductor. And the next year, 2014, and they have proposed a realistic setup where they have shown the giant thermoelectric effects in a proximity coupled ferromagnet superconductor device. Following them, another group, is Ozeta et al. In 2014, have found that we can have the thermal or higher thermoelectric figure of Merrick at the same time Seebeck coefficient in our ferromagnet superconductor junctions because they have considered some large accumulation of quasiparticles near the superconducting gas. I'm not going into the detail. So this proves that in literature there are many theoretical works which have already shown that a superconducting junction can act as a very good thermoelectric material. Not only theoretical works, there is some recent experiment which have already proved this fact. Like in 2016, Kollender et al., Stefan Kollender from Germany actually, they have shown that if they have considered the junction like a comet made up of copper, iron and aluminium. And these junctions, this junction can act as a very good thermoelectric material or thermoelectric current. But this happens in presence of high magnetic field. At the same time in 2014, the same group, they have shown that nonlinear thermoelectric effects can be found in a superconductor ferromagnet junction in presence of the high magnetic field. Can you see my screen? I'm still audible?
Yes, everything
Am I
is
still
clear.
audible?
Everything is
Okay,
fine.
okay.
You carry on.
Yeah.
No issues now.
Okay, yes, thank you. So in 2016, they have shown that the ferromagnet superconductor can act as a very good thermoelectric. The most importantly, in 2014's experiment, they found an excellent agreement between the theory predicted by Ozeta et al. They found the Seebeck voltage of the order of 100 microvolt per Kelvin. Now, with these motivations, actually, we have considered a ferromagnet superconductor junction, and we have shown that our junction can act as a very good thermoelectric material. But the difference in our work, or the most interestingly, we have considered some interfacial layer, which is responsible for the spin orbit interaction, the Rashba spin orbit interaction. And I will show you that due to this Rashba spin orbit interaction and some other factors, our junction can also act as a very good thermoelectric material. And later, in a very recent work, we have shown again that in the same junction, actually, if we have some unconventional pairing, so we call like frequency type of pairing, then that junction can also act as a very good thermoelectric junction in presence of those pairing. Now let me describe our model here. So we have a ferromagnet and the conventional PCS superconductor. And in between, we are considering a very thin layer which is responsible for the Rashba spin-orbit interaction. At the same time, which is creating some barrier. You can think about some quantum mechanical barrier height problem. But we are on top of that, we are applying some temperature gradient across the junction. So the base temperature of this junction is T. Now we are applying a gradient set delta T. So the ferromagnet is kept at set A plus delta T by 2 and the superconductor is placed at T minus delta 2 by 2. And since it's a ferromagnet, we can describe the ferromagnetic polarization vector with polarization by a vector is M. I will come to this point a few slides later. But the point is that we can have different kinds of ferromagnets and so we can have the different polarization. Also tuning the exchange potential, we can also have different polarization of the ferromagnet. We can tune that base temperature of the system because we want to keep the delta T as small as possible. We are not tuning that one. So we can tune the best temperature of the whole junction. At the same time, depending on the interfacial layer, we can have different Rashba spin orbit interaction. So the question is, our aim is to find higher thermoelectricity in this junction. So how much Rashba, which kind of materials should we consider, and what's the polarization of the ferromagnet, or which is the best possible polarization of our ferromagnet, or which is the best, which kind of materials are there? That I will come back to this part in the next slides or next few slides. Is it fine till still now? Am I audible? Can you see my screen? Change in the slide?
Yes, everything is fine.
Okay, thank you. So, before we have a, sorry?
No, please continue.
Okay. So, before we describe what is our results.
Let you know, ma'am.
Sorry?
Deepaknath, you please do not communicate with the resource person. Ma'am, please continue. There is no problem.
Okay, thank you. So if I, to understand that, what's the result that we have and how our junction can behave like a good thermoelectric, let us have a look at the junction which is called density of states at the normal metal superconductor junction. So for this slide, please forget about the ferromagnet, just consider a normal metal with a quadratic band structure, and we have a very symmetry between the up and down spin states. And in the superconductor, if we have a look at the density of states of the superconductor, we have a gap actually across which we don't have any density of state. And after that, we'll have some coherence peak and it falls down. So the question of this gap is called superconducting gap. And now, if we have an incident electron which is coming towards the junction, and then it will not find any state to transmit. If the energy of the incident electron above the gap, then it will transmit to the superconductor. But since it is a superconductor, what happens? Will instead of the single electron particles, actually we can have some pairs, which we call Cooper pair, where upspin and downspin can form a pair and pass through the superconductor. It can actually, this Cooper pair can carry the current. So let us have a look at the different types of scattering processes that can happen at this junction. In case of normal and the superconductor junction, if we have an upspin electron which is incident on the junction, then it can be reflected back from the junction, which usually happens in any kind of interfacial or any kind of barrier problem. And so this is called a normal reflection, or you can also call it an ordinary reflection. We can have tunneling like both electron-like and Hall-like quasi-particle, but because of the superconducting behavior of this material, we can have another scattering processes which we call Andreev reflection. This upspin incoming electron will take another downspin electron from the density from the superconductor, from the normal metal, and it can form a Cooper pair and pass through the superconductor. And because it's taking a downspin electron, so it will create a hole. So we'll have a hole of downspin, and that hole of downspin will be reflected back from the junction. And this reflection is called Andreev reflection. So we have 4 different scattering processes possible at this junction: normal reflection, tunneling like as electron-like and hole-like quasi-particle. We can have the Andreev reflection possible at this interface. Am I audible still? No?
Yes, ma'am, fine.
Yes.
Okay. Yes. Okay. And I'm very sorry for asking so many times because I have to check. I'm checking every slides. Okay. So now our intention is to consider ferromagnet superconductor junction. So what happens in a ferromagnet superconductor junction, in contrast to the normal metal, where we have some symmetry between the up and down spin density of states, in the ferromagnet there is actually asymmetry between the upspin and downspin density of states. Now, in the superconductor, I'm keeping the superconductor same. Now the problem is, whenever we will have this asymmetry or the imbalance between the upspin and downspin, and this asymmetry will actually modify the scattering processes happening at the junction. At the junction, we have some Rashba type of spin-orbit interaction, which spin-orbit interaction we can find in different types of Hebrew structures. We can have even in the semiconductor Hebrew structure. If this happens because of the potential gradient at the interface of the differently doped semiconductors, usually it started with this. If we have this kind of potential gradient, and this can couples with the electrons and give rise to a Rashba type of spin-orbit interaction. So for any crystal also, if we have we can have 2 different types of asymmetry. We can have bulk inversion asymmetry. At the same time, we can have some surface induces asymmetry. And because of those asymmetry, we can also have this spin-orbit interaction. But today I'm talking about only Rashba type of spin-orbit interaction. And mainly the material we are suggesting that the gallium arsenide based or this kind of materials, gallium arsenide, aluminium gallium arsenide or this kind of materials. Now here in presence of the spin-orbit interaction, so what happens, this spin-orbit interaction will, because of the presence of this spin-orbit interaction, the incident electron can flip its spin. So we know that there is actually, if in this junction we have an upspin electron coming towards the junction, we already know that it can be reflected back from the junction, which we call the normal reflection process. It can tunnel as hole-like or electron-like or hole-like particles, which we call the TE and TH. And we can also have some Andreev reflection, which I already mentioned in the previous slides. But in addition to those spin-conserving processes, because of this Rashba spin-orbit interaction, we can also have some spin-flip scattering processes. We can have the spin-flip normal reflection. We can have spin-flip Andreev reflection. We can also have spin-flip tunneling both electron-like and hole-like. That means if we have some upspin electron coming towards the junction, it can flip its spin and then reflect back. That is called the spin-flip normal reflection. And it can flip its spin and then form the Cooper pair and pass through the conductors. Then we will have it can also tunnel as an electron-like hole-like quasi-particle, but before that it can flip its spin and then tunnel. So we can have the spin-flip tunneling processes. And for the Andreev reflection, in addition to the normal Andreev reflection, we can also have this spin-flip Andreev reflection. So why I'm talking about, or why I'm bothered about these scattering processes, because of the presence of the polarization of the ferromagnet, the Rashba spin-orbit interaction at the junction, and also the barrier strength or this barrier present at this junction will modify the amplitudes of all these scattering processes. And as a result of these scattering processes, we will be able to modify the thermoelectricity or thermoelectric properties of this junction too. Is it fine till now?
Yes.
Okay. So I'm not going into any technical details. I'm not writing any Hamiltonian or any type of calculations, but I want to give you some simplified story out of these two works. But I want to show you some expressions which we have found for our system, which is the ferromagnetic superconductor junction. So the expressions for the thermal conductance, electrical conductance, thermal coefficient, and you can avoid looking at all the details. Just follow my words. I just look at this term, this 1 minus RH minus RE. And this is the only factor which is different from this one to this one and to this one. And there is a sign change of behavior too. What is RH and RE? This is actually the probability of the unbehaved reflection, or the amplitude of the unbehaved reflection is the amplitude of the normal reflection. Because the total amplitudes of all the scattering processes is conserved. So we can express all these thermoelectric coefficients in terms of this unbehaved reflection, normal reflections only, and it will take care of the rest of the scattering processes as well. And previously I have already mentioned that the Seebeck coefficient can be expressed in terms of alpha and G and the best temperature. Here you can see the expression of alpha and G, but whenever we are changing the polarization of the ferromagnet, we change the temperature of the system. Also, we can change the Rashba spin orbit interaction that will modify this RE, RH, and so on. And that will ultimately change the thermoelectric coefficients, electrical conductance, thermal coefficient, and also the Seebeck coefficient or the thermoelectric figure of Perry. Now let us have a look at the results for the thermal conductance. If here we are plotting the kappa as a function of T by Tc, and we are showing the results for different values of the polarization of the ferromagnet. Forget about the Rashba for this slide, and I will bring it up in the next slide. Whenever we are changing the polarization of the ferromagnet, actually the thermal conductance increases very slowly. But it is true in the low temperature regime. In the high temperature regime, the thermal conductance actually is slowly decreases with the increase of the polarization. And this is so there is a change in the behavior of the thermal conductance with the polarization. So this temperature scale, we call it a crossover temperature scale. So it separates actually two different behaviors of the thermal conductance with the polarization. Now this increasing behavior of the polarization of the thermal conductance with the temperature is not a very new one, or it's not very unique to our system. It's true for any superconducting junction. But this crossover temperature scale, or separating the behaviors of the thermal conductance with the polarization, is very unique for our superconductor ferromagnetic junction. And this behavior is true in presence of the barrier string too. This Z is actually the barrier, it's defining the barrier string. So this I have shown this result for in absence of barrier and also in presence of barrier. Even we increase the barrier string, it will increase. The behavior is almost same, but this crossover temperature scale will shift towards the upper temperature side or the higher temperature side. Now let us include Rashba spin orbit interaction. Am I still audible?
Yes, ma'am.
Okay. So in presence of Rashba, when we do not have any barrier string, so this thermal conductance actually decreases with the increase of Rashba. And this is true for all the polarization vector, but that means this is true for any kinds of ferromagnet presence in the junction. Now whenever we consider the finite barrier string, we'll have some non-monotonic behavior. So initially it will be increasing and then it decreases. So in presence of the barrier string, whenever we increase the barrier string, we will have this non-monotonicity. It's very prominent in our case. So the summary is, I'm not describing each curves again here. So just I want to draw your attention to the summary from this slide. The summary is, in presence of the barrier or Rashba spin orbit interaction and also the barrier string, we can have this non-monotonicity of this thermal conductance with as a function of the Rashba spin orbit interaction string. And I have kept the temperature or the base temperature of the system, like after this crossover scale, like 0.5 or something. But this was for thermal conductance. Now let us have a look at the Seebeck coefficient behavior. Again, it's monotonic or in absence of any barrier strain. But whenever we consider some barrier, in presence of that barrier, the behavior of the Seebeck coefficient is non-monotonic. Let us have a look what happens in an absence of barrier. With the increase of the base temperature, the Seebeck coefficient actually increases. Please only consider the magnitude. I'm not talking about the sign. So we can ignore the sign of the voltage for this for our case because it's same for all the parameter regimes. So it now increases with the increase of the temperature. At the same time, it increases with the increase of the polarization from the yellow towards the blue curve. In presence of the barrier, now we can see that there is a non-monotonicity in the behavior. So it increases, then it goes down. If we keep the base temperature around this, say 0.3 or maximum 0.25 or 0.3, then we can have very high Seebeck coefficients of the order of 3, or very close to T. And its presence it's true in presence of high barrier strength too. Now, so we can have what's happened in presence of Rashba. Now I'm showing here the density of density profile of the Seebeck coefficient. I hope I am still audible, right?
Yes.
Is it fine? Okay, yeah.
Yes.
So here I'm plotting the amplitude of the Seebeck coefficient as a function of Rashba and the polarization. Now we see that this yellow or the orange region is responsible for the higher Seebeck coefficient. Whenever we have this P of the polarization of the ferromagnet towards the P goes to 1, that means close towards which is often called the hub metal case. So very strong ferromagnet, we can have this higher Seebeck coefficient, but in presence of low but maximum moderate Rashba-Spinowitz interaction. So in order to have enhancement of the thermoelectricity out of this junction, we have to keep our Rashba-Spinowitz interfacial Rashba-Spinowitz interaction very low or moderate. At the same time, we have to choose the ferromagnet so that it's a very strong ferromagnet. Now, from the engineering point of view, we can also calculate the thermoelectric figure of merit, and I have shown here all the results both in, I think it's fine now. So both in presence of barrier strength and absence of the barrier. And in absence of barrier, there's again we are considering different values of the ferromagnet. If we just increase the values of the ferromagnets, the ZT will be increasing. And it's true for any type of Rashba and for all the TCs, T by TCs. And in presence of the barrier strength, we can see that actually initially it falls down and then is slowly rising. If we increase the barrier strength, it's actually more, the value of the ZT is higher than what we had previously. And now we should increase ZT, or that means the barrier strength further. Now we can see that we can have this ZT of the order of more than 4, of the order of 5. But we have to keep the Rashba either low or moderate. So we can have the enhancement in the thermoelectricity, and we can have the high, or the thermoelectric figure of merit higher than 1. That means our thermoelectric device can act as a very good thermoelectric device if we keep the Rashba-Spinowitz interaction, that is interfacial Rashba-Spinowitz interaction, very low or moderate. And at the same time, it's also possible to have higher thermoelectricity in presence of the barrier strength. Choose the ferromagnet material in such a way, or
Ma'am, we are not here. We cannot hear you.
Can you hear me?
Yes.
Hello?
Yes.
Yes,
Okay.
yes, clear.
So, okay, was it clear in the previous slide?
Yes, ma'am.
Okay, so here we have shown the nonlinear behavior of the Seebeck coefficient, and the thermoelectric figure of merit is very high in our case. That means our ferromagnet superconductor junction can act as a very good thermoelectric. And why does it happen? have shown that because of the interplay of the Rashba spin orbit interaction, polarization of the ferromagnet and the barrier string, and the idea of exploring this interfacial Rashba in the context of thermoelectricity is very unique actually here. So we are hopeful for some recent or some upcoming experiments too. And if you want to have a look at the details, please have a look at both of these papers. And anytime questions and comments are welcome, you can write to me as well. And thanks all of you for your patience and also bearing with me because I had a very bad internet connection today. Sorry for that.
Thank you, Dr. Paramita Datta, for a nice lecture. So here are some questions actually from fundamental level questions from student section actually. So can I go for it?
Yes, sure.
Okay, so first question is from one English student. So he is asking that what is spin current?
Oh, okay. Spin current, that means, so I can just simplify, I can tell you something like this. Suppose we often have a conductor and we see that the charge current, we do not consider the spin in that case. If we have an imbalance between the upspin and the downspin electrons, then you can see that but electrons of one particular spin is flowing to that conductor. That means if you have, suppose you have a upspin electron flowing to the conductor. If in this way, if we can separate electrons of any particular spin, then we will be able to find this current. We call this spin current.
Okay. So the next question is what is the significance of thermoelectric figure of magnetism?
Yes, actually, it's. I hope you are already aware of the efficiency of any device. In the thermodynamics, we often define the factor like efficiency. It's very similar. It's very analogous to the efficiency. It's actually it will give us the efficiency of that thermoelectric device. It's hard to show you the calculation right now. It's actually. Give you the ratio of what is the output power to the input power. Input power you have to provide continuously to maintain the temperature gradients, and that ratio is called the thermoelectric figure of merit, and you can think about it's very analogous to the efficiency of any device.
Okay, so another fundamental question from any student section. So what is Rashba spin orbit interaction?
Yeah, so as I mentioned in the slide while describing the Rashba spin orbit interaction, if you are in a crystal, if you have some bulk inversion asymmetry, or you can also have some surface asymmetry, and if we consider this kind of junctions, suppose you have two semiconductors, and because of the two different materials, you will feel at the junction there will be a potential drop. So, or we can see the potential gradient that will give you the delta V, and out of this delta V, when it couples with the electrons, that actually gives us the spin orbit interaction, or we can say the spin orbit field. That will be, in our case, it's actually, in any case, actually, it will be able to flip the spins of the electrons. In our case, the incident electrons, of course. And we can also have this kind of spin orbit interaction